Picks up the room perfectly.
Hello?
Do it again.
Hello?
Yeah. Yeah.
Okay.
Are we? So we're right.
Yeah.
This is not your job. This is not my job. What's our audio video? So should we read any of this or leave us? Just leave us. Let's go. Yeah, let's go. Leave it. Just
This mic's off.
Yeah, I forgot. It's a, I don't know if Winston still has it, but that one, using that one. He's currently off, but yeah, no. This is off, see?
No, it's off.
Is it? No, this is awesome. It's on now. Oh, yeah. There you go.
Something's happening on.
That was pretty, it's like during Winston's presentation that he had that fucking. Yeah, he was like fucking feedback. Yeah. Alright, let's go to the show you go.
feedback? Yeah, there is.
So it's not this one, this. Yeah. Hello, that's not doing it. So it's the mics. Show me the feedback. Is that on?
That's not, that was not.
That's good feedback. That's good feedback. Well, that's because it's here. Just turn it down. Turn your volume down. Let's pick up, there's an ambient mic. Your mic, and just try them power. That's what I want to care about. Just speak.
Hello? Hello?
So what's the problem with that?
What's the
Oh,
ambient mic?
yeah. Just hit the.
What's that ambient mic?
So does it give any, what's the problem?
Don't you hear like that?
There's a bit of that, so you can turn off the ambient mic.
You know what I'm saying?
So let's try one at a time. Okay, position check. And that's which one, that's why I was doing that.
There's no feedback.
Do this.
Yeah.
Can you hear anything?
Yeah.
All right, we get it. There is,
Hear that?
I can hear the knocking, but like there's no feedback or anything.
Where's that coming from? Just-
there's a, I guess the mic on the computer. This was too much. Here, this, this. Can you still hear the live stream? Just keep
I can still
tapping.
hear you talking.
Okay, we're gonna do this.
It does matter.
I how particular you guys are.
It's like the fun is this is scary.
Proactive exams. Yeah, Lucas.
I just want to go.
So overall,
There's noise.
because if you get a bit of echo, there's like an ambient mic, which I can't isolate. This might be, that's off.
Did I? Oh, that way. I'm sorry, they have.
Actually, so much different. Yeah, low-key.
There's a mic. What is this? So there's a mic, I think on the PC, right? That's what I'm. So we're talking on that, is there a lot of background?
I don't think so, but I just.
Yeah.
Well, just, it's only if you get the desk. It's
You know-
an issue.
So don't hit the desk.
Ready to go.
Really?
Shouldn't be a lot of the.
Oh, man, come on. You have the best audience. Like, you could be at a Republican town hall.
Yes, but-
Good.
Yes, it's true. This one?
Is that one, is that the one that's plugged in? I don't think that one's plugged in.
This other one?
Yeah, I think so.
Topic.
It's just, there's a mic under the.
Yeah, there she is. Is it the top arrow?
Into your computer.
Oh, it's the bottom arrow?
How'd you get this to work?
Is there, did you turn the little?
Yeah, so there's the power bar. Yeah, that's. You plug it right there.
And make sure the power.
So how you go forward is the actual, she's on now, and then you kind of go with that.
Yeah.
Here we go.
Eight?
No problem, yeah.
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 There you go.
Yeah, I guess so.
Good, here. All right, welcome back. We are continuing on with our naval architecture technology and marine mechanical design presentations. I'd like to welcome those who are online watching the YouTube stream. Sorry about the audio. For the first couple of presentations, but I think we have our problem ironed out. Do we, Dave? Yes, we have our problem ironed out. So we're going to continue on here, and this morning we have Isaac Nickerson. Isaac is going to tell you all about his Coast Guard vessel, and it's a great audience. They're going to love it.
Yeah.
So relax, it's going to be good.
Yeah.
Isaac, all yours.
So, like Winston said, my name is Isaac, and I did for my design project, I did a 63.2 meter fishery research vessel. So, just a quick little overview of what we're going to go over today. We're going to go over the introduction, some state-of-the-art analysis, the line development, general arrangement, powering, electrical, structure, capacity plan, capabilities of design, stability, cost estimate, and then we're going to close it off with some closing comments. So, for introduction, my vessel is the CCGS Francis Crozier. It's an offshore fishery research vessel operated by the Canadian Coast Guard as part of the National Shipbuilding Strategy, a federal initiative to modernize Canada's marine fleet and support the shipbuilding industry. It is the fourth vessel in a series of offshore fishery science vessels following the CCGS Sir John Franklin, the John Cabot, and the Cartier that was in the harbor this past week. And it will work alongside of the Franklin off the Pacific coast of Canada. We built by Seaspan Shipyards. It is designed to operate up to 200 nautical miles offshore off the Pacific coast, supporting scientific missions like fish stock assessments and oceanographic sampling. It has a range of 7,500 nautical miles, an endurance of 40 days, and a max speed of 13.5 knots. And it features a drop keel to deploy sensitive instruments below the bubble zone for accurate data collection. I chose this project because I grew up around fishing vessels, and I've always been drawn to the working boats that support our coastal communities. Designing an offshore fisheries research vessel felt like the natural fit for me. It combines my personal connection to the fishing industry with the technical challenges of naval architecture. This project gave me the chance to contribute to something meaningful, a vessel that supports science, sustainability, and the future of our oceans. So here's the state-of-the-art analysis. To develop this vessel's proportion, I compiled a state-of-the-art analysis using data from similar vessels from the Clarkson's World Fleet Register database, and particularly like the vessels I particularly chose were fishery research vessels, oceanographic research vessels, and trawlers. One of the key references was the CCGS Sir John Franklin, which, although it is an icebreaker, it shares similarities in mission and structure. I also used empirical formulas and regression methods from sources like Ayer, Postelijn, and Schneeketh, to name a few, to cross-check values and ensure consistency with established ship design methods. A limitation of the SOTA was the lack of directly comparable vessels, as well as the lack of overall data. Most similar vessels were icebreakers, and which tend to have a greater displacement and lower block coefficients. So this made it necessary to interpret the data carefully and prioritize the vessels that were ice strengthened rather than ice breaking. Additionally, many empirical formulas were used many empirical formulas that were used were not specifically developed for research vessels, so they only provided general guidance rather than definite values. Despite these challenges, clear trends emerged. For instance, there was a consistent relationship between the deadweight and the LOA, as well as between breadth and displacement. These trends helped the vessel's dimensions with a reasonable range. Most vessels fell within a CB of 0.55 to 0.6, supporting my choice of a 0.6 block coefficient. And the draft values also fell around 4.3 meters for vessels of similar length and displacement. And on the screen there, I have my final design parameters, which was a length overall of 63.2 meters, a length on the waterline of 60.3, length between particulars of 57.3, breadth of 13.5, depth of 6.3, draft of 4.3, a freeboard of 2 meters, a block coefficient of 0.6, and then a displacement of 2,200 tons and a deadweight of 700 tons. So now we're going to look a little bit at the line development. So the chosen hull form is a round bilge design with a bulbous bow and is Lloyd's 1A ice class. The round bilge shape offers lower resistance at moderate speed, which improves fuel efficiency and seakeeping, both critical for a vessel with a 40-day endurance, often operating at low speeds. The bulbous bow was selected to reduce wave-making resistance and help meet the vessel's top speed of 13.5 knots. Given the operational area on the Canadian coast, ice strengthening was necessary to allow safe operations during the ice seasons, though the vessel is not intended to break ice. The hull form was developed using parent lines derived from several proven research vessels, adjusted to suit the vessel's specific mission profile and propulsion system. A sectional area curve was generated to evaluate displacement distribution and refine hull shape. This curve was iterated alongside power requirements, hull resistance, and interior space needs. So for the vessels that I chose for my parent hulls, I chose the Celtic Explorer, the Tom Crean, and then also the that's my boat, the Sir John Franklin. They also use similar diesel electric propulsion systems, operate at similar speeds, and have comparable hull proportions. The Sir John Franklin, in particular, provided valuable insight due to its service in the Canadian Coast Guard and its shared fleet purpose. So yeah, there's another image on the screen there of the line split that I developed, and you'll see that my bulb is on there as well as I have a stern bulb, like Ashton was mentioning earlier. So, and this is also another graph to prove for my bulbous bow that it was needed for for the efficiency, as you can see, I have a Froude number of 0.286 and my block coefficient is 0.6. So that puts me in that star range, which is about 5 to 10 of efficiency increase for that design. So now we're going to have a look. There's my general arrangement that I conducted. So you can have a look there throughout when I'm going to pull up a few new slides, but that's the overall profile view there. Here's the working deck and the main deck, and you can see, I don't know, can you guys see that in the back? Is that visible? Yeah. So as you can see on there, we have the covered forecastle up at the front. We have some cabins going aft, and there's also a few different science rooms, such as the ocean winch compartment for the CTD rosette that will be deploying off that side. There's a lab control room. There's a wet room. There's 2 working decks that extend on both starboard and port side, with your main trawling deck on the center line. And then there's also 2, if you look down the main deck, there's 2 port trawl door rooms on the aft for the trawl doors. And then there's also different various workshops and also just a few more rooms, there's gym, freezer, fridge, galley, you name it, just like a generic vessel. Oh, that lag. Good. Oh, there we go. So there's the lower deck and the tank top, and you can see the different compartments as well there. So for my lower deck, that's where my wet lab is, and there is a fish hopper on the main deck on the center line that all the fish will be flowing down into the wet lab from that hopper. Then there's the upper machinery flat, the VFD compartment for the diesel electric setup, the control room. There's a few different workshops, domestic control rooms, and then up front we have the engineer's office, a few different tool stores, and then we also have the bow thruster compartment. And down the tank top, there's a few different machinery, which we'll cover that when we get to the machinery section. And then here is a view, not so detailed, but it's of my upper decks. There's not a whole lot going on up there. So you have the bridge deck with your center console, your chart table, and a staircase, and then there's also a washroom as well there. And then the unique part of mine is that there's also a mammal observation tower above the bridge, which there would be a vertical ladder inside of the bridge that will allow you to go up into there and have a little overlook of what you're looking at. So next we're going to look at the powering for this report, for my design project. So for the powering, I use the Holtrop and Mennen method, which is a well-established empirical approach for estimating ship resistance and powering. It was chosen for its accuracy and versatility, particularly for vessels like research ships. The total resistance was calculated by summing multiple components, including frictional, wave, air, appendage, and bulbous bow resistance, followed by a 15% service margin. This yielded a total resistance of 140.18 kilonewtons and effective power of 973.5 kilowatts at 13.5 knots. So like I said before, this vessel uses a diesel electric propulsion system, and it'll be driven by 3 Caterpillar 3512C gensets, as you see pictured on the screen there, and they're each rated at 1786 kilowatts at 85% MCR. This configuration was selected for its operational flexibility, quiet running for its research activities, improved fuel efficiency and space efficiency. The propulsion motor, as you see down, as the blue one down there on the bottom, the propulsion motor requires 1,585 kilowatts to turn a 3-meter 5-bladed fixed pitch propeller at 193 RPM with an efficiency of 58%. A 610 kilowatt bow thruster was also included for added maneuverability during low speed operations and navigating around different trawling operations. While not directly related to the propulsion, this vessel also includes several auxiliary features that are critical for the mission performance. So like I said, the bow thruster for enhanced station keeping during trawling or sampling, and bilge keels would also be designed in the next design iteration for roll reduction to ensure stable working conditions on the deck. So there's a little bit of my machinery arrangement. So it's kind of, as I mentioned before, you have the steering flat aft, and then also the wet lab there as well. And then I have an upper machinery flat with my 3 gensets down on in the middle there. And then I have the 2 compartments for the variable frequency drive and the control rooms. And then there's also different various control rooms for any machinery on the deck. And then in the tank top, you can see a few more bits and bobs of the different mechanical equipment that we need, such as heat exchangers, pumps, hydraulic power packs, you name it, it's there. So next, we're going to look at the electrical. So the vessel electrical system was designed around 3 operational load conditions: in transit, fishing, and emergency. So the highest demand occurred under the fishing condition, which peaks at 5,684 kilowatts. So to meet this requirement, this vessel was equipped with the 3 Caterpillar 3512C gensets, and they're each rated for their maximum load of 2,100 kilowatts at the 1,800 RPM. So this provides a total generating capacity of 6,300 kilowatts, which was above the peak demand. So, and that ensures redundancy and load sharing flexibility, as well as a safety factor within the maximum power output of the gensets. So in the emergency generator that I chose was a Caterpillar C18 rated at 301 kilowatts at 1,500 RPM. It's located in a separate compartment, which if I go back one slide there, nope, that was the wrong slide. Sorry about that. But it's located at the main deck on the port side next to the stack. So, and it's fully isolated from the engine room in compliance with the SOLAS and Transport Canada regulations. And this ensures survivability and automatic start capability in the event of a main power loss. It's sized to meet the vessel's emergency load demand of 104 kilowatts, powering critical systems like the lighting, communications, fire pumps, and different navigation equipment. So that one's probably not going to be able to see, but that is my single line diagram that we did for the electrical. So I did enhance it so we could maybe see, is that clear better there, that one? Yeah. So we can see the different main propulsion bus bar that you see there with the propulsion motor, the variable frequency drive coming off of that. And then you also have your main the main gen sets, which is the Caterpillar 3512Cs that run onto that main propulsion bus bar. And you can see all the loads being trickled down off of that. Next up is the structure. So the vessel is constructed from marine grade mild steel with localized use of higher tensile steel in high stress regions and the ice belt regions to meet Lloyd's 1A ice class standard. It is designed in accordance with Lloyd's Register for Ships and regulations and complies with Transport Canada and IMO Stat 4 and 6 requirements. This vessel is transversely framed, which was chosen due to its moderate size and structural complexity, which is introduced by loads of deck equipment and features like the drop keel. Transverse framing simplifies the construction, improves the shape control in the bow and stern for smaller vessels, and allows for easier integration of bulkheads and watertight compartments. Some of the special features in the structure aspect was the ice belt reinforcement at the waterline using thicker plating and reduced frame spacing. Drop keel housing requiring specialized insert plates and strengthened support structure, and watertight bulkheads to subdivide the hull and meet the damage stability requirements. So designing around the drop keel housing was one of the most complex tasks. Ensuring strength, continuity, and watertight integrity in that region required reinforced structure and carefully aligned stiffeners. Other challenges including routing systems through watertight bulkheads, and while maintaining compliance and applying ice strengthening without exceeding weight limits to compromise the vessel's center of gravity. So that was the 3D model that we did for our structure that was done in Express Marine. As we seen with Ashton's earlier, that's how we modeled all of our structures. We did it all 3D, which was really cool to do. And there is a quick look at just a little sample of some of the structures. So that would be the midship profile, and you can see all the different intricate pieces. So the right-hand side would be a deep frame, and the left-hand side would be an ordinary frame, with pillars being one of the most tedious tasks that I had to do. And they are everywhere in my structure arrangement. So there's just a few different dimensions there, mentioning some of the structure pieces. So next we're gonna have a look at the capacity plan. Again, it's hard to see all these things because they came off a drawing, so it's a little bit tricky to see, but I hope that it's somewhat visible. So the main capacities for the capacity plan was the fuel oil at 481.6 cubic meters, ballast water at 371.6 cubic meters, and fresh water at 29.8 cubic meters. So how these capacities hold up against what was required for capacities. So for the fuel oil, the vessel consumes 358 tons of fuel over the 40-day endurance and at a density of 0.89 tons per cubic meter. This equals about 406 cubic meters. To allow for the 30% service margin, the vessel should carry a minimum of 465 cubic meters to cover all the 5 operating modes, which include port, transit, heavy lifting, heavy light trawling, and standby, and with a buffer for any unexpected demands. So the capacity of 481.6 meets that number. For ballast, 313.8 was the minimum based on a 39% ballast to dead weight ratio that was found from the state-of-the-art analysis of similar vessels like the Sir John Franklin. The capacity of 371 also meets this number. And for freshwater capacity, I have 29.8 cubic meters, which is enough to supply 36 people at a rate of about 100 liters per person per day for approximately 1 week. This sizing decision was intentional. So the vessel is fitted with 2 freshwater makers to allow to reduce the size of the freshwater tanks. And this was done as if I would have went with the 40-day endurance, it would have been approximately 144 cubic meters of freshwater. And I wanted to get that number down to allow for space for other aspects. So now we're going to look at some of the capabilities of the design. So this vessel was designed from day one to meet the unique operational needs of a Canadian offshore fishery research platform. Some of the key features included, like I mentioned before, the drop keel for deploying some of the scientific instruments below the bubble zone, essential for accurate sonar and acoustic readings. The diesel electric propulsion systems offering quiet and efficient operation, ideal for both transit and sampling modes. Ice Class 1A construction, enabling seasonal operations in ice-infested waters. 2 freshwater makers, allowing for the vessel to operate independently for 40 days. Flexible lab spaces and accommodations for up to 16 scientists, making it a true multi-role research platform. So just a quick little operational overview. The Francis Crozier was going to be operating on a mission-based deployment model, meaning each mission looked very different. From different salmon migration tracking to any deep water trawl surveys or even oceanographic sampling. Still, there's just overall there's a general rhythm of how the day kind of would go. So morning would kind of the morning would be kind of on an acoustic equipment is being deployed via the drop keel to begin surveying fish populations or different seabed profiles. Oceanographic tools like the CTD are launched to gather temperature, salinity, and depth data. In the midday, you would be looking, depending on the mission, the vessel may shift to different trawling operations, collecting different fish or plankton samples. Scientists would move specimens directly to onboard wet and dry labs for immediate processing and analysis. And in the afternoon, the ship may transition to the next station, conduct more sampling, or just be calibrating into various instruments. And all the while, all the crew members are taking logs and maintaining systems while the researchers are refining the data for accuracy. So while each day's tasks may vary depending on the mission at hand, the vessel's design allows it to adapt seamlessly, supporting both biological and environmental research in some of Canada's most demanding marine environments. So next, we're going to have a look at the trim and stability. So for the InTract trim and stability book, a total of 6 different loading conditions were assessed. So these conditions were assessed using general hydrostatics to adhere to the IMO code on intact stability. And some of the loading conditions that were assessed include light ship departure, mid-voyage, port arrival, cargo operations, which unloading and loading different cargo via the cranes on board, and ice accretion for the worst load cases. So within these various loading conditions, multiple tank loading conditions were assessed as well. So various different percentages of tank levels were done. So from varying, so like I said, different consumables, different cargo levels. So this comprehensive range ensured that the vessel's behavior was understood for the master and owner across all realistic operating profiles. So I have 2 images from the from the stability that was done. So we have on top there, we have the mid-voyage at 50% consumables and 100% cargo with ballast. And from there, we had a draft of about 4.64 meters, trim of 1 degree aft, and a heel of 0.42 degrees to the starboard. For the ballasted cargo operations at 10% consumables and 100% cargo with the ice, we had a draft of 4.73 meters, trim of 1.34 degrees aft, and a heel of 0.25 degrees to the starboard. So the last thing we did was the cost estimate, and the cost estimate for this vessel was done using the CARIAT method, which estimates labor and material costs for steel work, machinery, outfitting based on the vessel's parameters. And although it's effective for early stage estimates, this method produced a lower total cost than expected due to its exclusion of modern cost-effective science equipment. This type of specialized equipment, which is common on research vessels, has risen sharply in price since we all know COVID, and is not captured by the outdated cost data on which that method relies. So from the Carriot method, the total cost of the vessel was found to be approximately $30 million USD or $45 million Canadian. So, but based on comparable builds, market data, the realistic cost, construction cost for a vessel of this class, which is an ice class diesel electric fishery research vessel, to be built in North America via Seaspan, it would likely be in the range of anywhere between $80 to $100 million USD or 110 to $140 million Canadian, and that is for all the different scientific equipment that is on board. So, and this kind of more resembles what the actual cost of the CCGS Sir John Franklin and reflects the premium for custom outfitting, labor, and regulatory compliance and different scientific equipment. So finally, we're going to go over some closing comments. While this vessel successfully meets its operational goals, there are several areas where further development definitely could improve the final design. So drop keel integration, the drop keel is a vital part of this vessel. And if more time would have, I would spend more time researching similar systems. And if more information were to be made, because a lot of the information on the drop keels is proprietary. So you actually can't get a hold of it as a student unless you have a checkbook in your hand. So I could actually analyze dynamic loading and different structural reinforcements, which would be beneficial to ensure long-term reliability and performance. As I mentioned before, the bilge keels development. So bilge keels were considered as a means to reduce the roll and improve the seakeeping. However, they were not yet sized or detailed. So with more time, a hydrodynamic analysis could have been conducted to properly design their size and placement, balancing roll dampening with minimal added resistance. Finally, the structural layout and the weight optimization. So structural design was constrained by time and different energization limits. So with further development, a more efficient internal structure and improved weight distribution could have definitely been achieved, potentially enhancing stability, trim, construction efficiency, you name it. So kind of like I mentioned in my trim and stability, I maybe could have got those values to be more on an even keel. So these improvements would not change the vessel's mission capability, but they definitely represent areas for refinement in future design cycles. So that concludes my third year design presentation. If there are any questions, I'd be happy to answer them now. Ashton.
Yeah, kind of going back to the closing or your capabilities design, how far below base does the keel extend into the sea?
I wish I could tell you that.
Okay.
This is another thing, it's all proprietary information. So they're not going to tell you how far we can do, what we can do, what depths we can get to, right? Because then then the next guy over is going to see that and he's going to be like, okay, well, if we beat that, then we can take their market as well. Right?
Great presentation.
Thank you. Winston.
You mentioned that you selected your engine for how quiet it is. Is there any other equipment or designs on the ship that help in its mission specifically that you'd like to highlight?
Aside from the quiet, there is also the diesel electric, like you had mentioned before. The diesel electric system is a very versatile system. You can position different pieces of equipment throughout your vessel and achieve, you don't have to have a straight shaft running down through the entire vessel. You can position things where you'd like to have it and save a lot of space. And also Caterpillar, for the NOx and SOx emission standard, they also have tier 4 engines ready to go out the gate now, and that comes pre-installed. No scrubbers needed. It's just a part of the engine configuration. So that would set you up for the future, and you wouldn't have to upgrade it in the future.
Absolutely. Sounds good.
Ian.
So further to that, I guess something we went through, I considered, I don't know if you went through it, looked at, is in some of the operations going in what we call, I guess, wires.
Yeah.
Stuff, running on batteries at home.
Yeah.
So you're running your electric motors just in a battery mode.
I haven't actually looked into that, but I also did overrate my engines for what they need. So there's definitely a margin there to actually bring myself a little bit lower. So you're not going to be running it at full RPM.
So, what I mean is you would install a battery bank.
Oh, an actual separate battery bank.
On battery mode, that's all fine.
That was definitely a thought. Me and Phil have been mentioning that throughout the years. Just for the last year there, just different operations where we could maybe throw in batteries to maybe take that diesel electric next step and actually get that electric.
I've seen some of that, I wouldn't go trend, but there may not be a need for, this is deployed, this is, let's go through this.
Yes, yes.
Not familiar with what the issues are, farmers there for doing that, but yeah, there is, you see that in some of those.
Yeah.
And given it's diesel electric, it's something that potentially could be.
Yeah,
benefited.
definitely see
It's a
something.
Space issue.
Yeah.
Mostly, but having a battery bank that will offer
Yeah,
a nominal amount of time to be able to do that stealth.
Yeah.
Stealth is not meant to be for more just.
Yeah.
silent mode
Yeah.
or-
so yeah, it's not currently something that they have on the other members of the fleet, but I could definitely see that in the future, kind of taking that next step to kind of go towards that more battery bank, more electrically designed vessel type of idea. Yes, Sean. Thank you very much.
The drop keel is an interesting design feature. Any specific reason as to why you went with that versus the traditional on-hull array of sonar?
Yeah.
You didn't know them.
Yeah.
Design requirements.
Yeah, no, absolutely. So there's a little zone that's presented underneath your vessel, and if you actually drop your equipment into that, you could potentially damage it while it's actually going in. So when you actually launch it down a little bit deeper, you just mitigate all that risk, and you're also getting way more accurate samples as you get further deep away from the actual engine and from the actual vessel and the engine vibrations and different effects that the vessel has on the water.
So it's understanding of better data.
Yes, absolutely. Absolutely.
Well done, thank you.
Thank you very much. Is there any other questions or anything? Nope. Okay, thank you very much.
I'm like in the desk, so I'll wait for the next time. I don't know why that's
Yeah, is that on the, Ian, we can turn off the screen? Yeah. What is that? Yeah. Yeah, you go, keep going. The question we see at the last two numbers. So, yeah. Oh, is the. Good. All right, thank you, guys. Here you go. Thank you. Oh, yeah. Stole the picture, ran out the door.
He's got back there on the property.
That's right, he's down. Gone to the airport.
Yeah, he's already done
He's got some change. Yeah. I would too. All right, next up, we have another naval architectural technologist. For the real estate budget, we have Skylar Wheeler, who is going to tell you all about her design project.
All right, so like Maxim said, my name's Skylar Miller, and I'll be walking you through today my 1100 TEU container ship project. So before we jump right into things, this is a little overview of what we're going over today. So an introduction to my vessel, just with some parameters and where it's actually being used, and then just a little information on SOTA, which is just state-of-the-art analysis, and why it was used and how it was used for utilizing and coming up with parameters. Then we'll talk about the hull form development and different aspects and why I have certain features on my hull. Then we'll go into my vessel's final general arrangement, and then again the powering, propulsion, and a little brief introduction on the electrical systems. Then we'll talk a bit about on the structure, what registry was used, what steel was used, where it's being constructed, type of thing. Then we'll be going over the capacity plans specifically for the tanks, and then we'll move on to other capacities like fuel and stuff. And then we'll do a cost estimate, and then last I left trim stability since I have a bit more to talk about on that. So to hop right into it, it's just a little introduction to my vessel. So my vessel is a 1100 TEU container ship, and TEU, for those of you that don't know, it stands for 20-foot equivalent unit, measures in 20 feet in length. This is a very standard measure used in the shipping industry. So there's two really standard types of containers, but 20-foot equivalent unit is the basic one that we see a lot here in St. John's. So my vessel will be sailing directly between Halifax, Nova Scotia, and St. John's, Newfoundland as a direct one-way trip each time, and it was being designed for the OceanX fleet here in Newfoundland. So this vessel will increase shipping efficiency here in our province, as well as increase cargo flexibility, as my vessel has a reefer capacity of 150 reefers, and another shipping industry term, reefer just stands for refrigerated container, so they can be chilled or heated depending on what type of cargoes in those containers, I chose this project of container ship as the ship type really highlights practical design, but also design challenges that are seen. So like, especially here in St. John's, the Narrows, as we know, it's called the Narrows for a reason. It's 61 meters at its narrowest point across, and it has a draft restriction of 11 meters. And if you've ever gotten the chance to see the OceanX boats here, do the 360 in the harbor, it's a very cool thing to watch. It's these huge ships just doing a full 360 on one point is really cool to watch. This is just the route where we'll be going. So you can see it starts off St. John's and goes straight to Halifax there. So just a little look at my state-of-the-art analysis. So SOTA was used to utilize and find data from existing vessels of my container ship type. And as we know, there's hundreds, if not thousands, of container ships out there, all different lengths and capacities. They go up to, I think it's like 90,000 TEU now, I believe. Now, we're obviously on the smaller side because of the Narrows here. So it was quite easy to find other ship data parameters for my state-of-the-art analysis, which was really nice because I had about 130 data design points. Now I did have to sort through a ton. There's about 1,000 that I narrowed down. I was like, okay, I can't use all of these. I have to narrow down somewhat. So I came down to 130 with the TEU was ranged from 800 TEU to 1,500 TEU. So you can see right here on the side just some graphs that were used, deadweight versus length overall, which helped me get some of my parameters. And then on the bottom there, it's a length overall versus the TEU capacity. So with the SOTA, I was able to come up with some final parameters for my vessel, a length overall of 148.5 meters, a beam of 24.7 meters, and an overall depth of 12.2 meters, and a draft of 8.2, which, as I said before, the draft restriction here in the Narrows is 11 meters, so our draft satisfies that. We have a freeboard of 4 meters, and the container capacity is 1,100 TEU, as I stated before. A top speed of 18.8 knots, which is common for container ships as they are needed to go pretty fast, and then a cruising speed of 14.5 knots, and she can hold 19 souls on board. So moving on into some of the hull form development. Starting off this project, I knew the whole form would be a challenge as meeting my container capacity, the speed, and also being able to meet my lock coefficient for my vessel type was going to be a challenge. So to achieve these three requirements, when I was actually starting off, I knew it was going to be a bulbous bow. So I went with an oval-shaped bulbous bow, as you can see here on the bottom. The bulbous bow really provides weight resistance and enhances speed and fuel efficiency and performance overall. For also on the stern end of my vessel, I have a stern bowl placed, which really helps with weight flow and just drag and all that. This will also help have very positive effects on fuel efficiency and propulsion. So to develop the hull form, we use Maxarf Modeler to create and form the first iteration of the hull. And Maxarf is really useful. It gives the ability to tell you the hull's parameters like block coefficient, displacement, and all that. So there's a lot of back and forth going between, like when I would change something, okay, I have to make sure my block coefficient is met because container ships need a certain block coefficient to achieve their speeds. So Maxarf is really, really helpful with the fact that you can go back and forth and check, and you can kind of move your control points, figure it out very nicely. So moving on to the general arrangement, just a bit before I jump straight into it, just some notes on the general arrangement itself. So I have 8 container holds in total. I have 1 aft only above the deck, and I have 7 forward of the superstructure, which are below the deck and above the deck. The wheelhouse is the superstructure, which is on top of the wheelhouse, is important to keep in mind with container ships because you have these huge stacks in front of your wheelhouse. You need to make sure you can see over it. So the SOLAS line of sight regulations is very important, which I'll get into in the next slide. We have 8 accommodation decks, which is a fair amount for the size of ship, but where it's a lot skinnier than most superstructures, we were still able to fit all accommodations needed. And then we have 3 tiers of machinery space, which is mostly because for overhead maintenance and repairs. So this is just the second slide of my general arrangement. So now we're going to take a quick look at my profile view. As you can see right off the bat, the SOLAS line is right there on top. This was very important to keep in mind when first designing, just because SOLAS states that you need at least 2 ship's length or 500 meters of unobstructed view above towards the water, whichever is less. So mine would be 297 meters since my ship is about 2,500 meters in length. So next, this is just some midship views. You can see the one here on the right is directly at the midship section where the parallel mid body is quite massive, so I can really fit all my containers there. But the one on the left, as you move forward towards my bow, it gets a lot narrower due to the bulbous bow shape. You can see we just constructed some steps and stools in there to make sure containers fit properly and securely so they're not moving around and all that. So above here we have my main deck. This is where my hatch covers are placed. You can see all the holds on top. And then after that is my accommodation block where I would have my change room for my engineers on board. We have an engineer office next door to that, as well as a workshop and a few other stores there. We also have, you can see just behind my first cargo hold, you have your cargo control room. And I put it here because it's very close proximity to all the cargo holds, which is very important. We also have my emergency generator placed here to keep it above the water line. In case any flooding happens, you can still use it, you can still switch on. And then we also have some provisions kept here, which is one of the things that was a disadvantage with container ship. You can't keep all your provisions in your kitchen, your galley, and all that next to your galley, which kind of sucks, but we have a crane and a manhole, hatch cover there so we can actually bring those up. And then below there we have our second deck. You can see right away that my hull form really starts to get skinnier as you go down because of my bulbous bow. This is where the engine room first, this is the first tier, and this is where you get a lot of the overhead space needed for maintenance, like overhauls, anything you need to do maintenance on pistons and stuff like that. And here, there's a lot of white space, but this is where a lot of machinery, you have the many manifolds, pumps, stuff like that. So next, above here, we have my tank top. This is where the engine will sit directly on, my main engine. And then you can see a lot of my ballast tanks there as well. Moving to the left-hand corner, we have my engine room flat. This is where my gensets will sit, as well as there's a few cutouts that are seen for my main engine, again, for overhaul and stuff. And we have the main engine control room there as well, which is pretty far aft. In the middle there, we have the poop deck, which is just where the two different messes we kept, the officer's mess and the crew mess. It's very common to see them like separated, but usually they do eat together. And we have the galley there as well. And just up front, just a small drawing of my forecastle deck, of my mooring arrangement, my container, and my chain locker and stuff. And now finally, accommodations. Like I said before, we have 8 tiers accommodations, which is quite a lot, but we were able to utilize that space quite well. This took a few iterations to go here to actually utilize the space nicely, just because there are so many decks. But we have 20 cabins, which is really nice because we have 19 souls on board. We have a fair bit of recreation to keep the crew happy, I guess. We have a recreation room, theater, and we also have a gym there. And on the top left-hand corner, we also have the 2 different day rooms for officers and crew. Again, that's very commonly seen, but they usually do hang around each other. You can also see my wheelhouse there in the bottom right, and then the wheelhouse top as well. So a bit on the powering and propulsion. For the powering and propulsion part of this project, effective power estimate was done using the whole drop method as well as estimate using Keller's formula. This was a tedious process, but it came out to give us quite an accurate reading, which was nice. Once the estimate was completed, we were able to fit our engines, and for my ship, I fitted it with a Wärtsilä 14V46F, which is an output of 16,800 kilowatts, and she is a medium speed diesel engine, which she is a faster vessel, and this is why we need so much power, considering it's a container ship. Cargo vessels really need to keep that speed going when we have so much fresh products and stuff on board. And then she's fitted with 3 different gen sets, so she has 2 L2131 DF at 1,700 kilowatts, and then 1 9L2030 at 1,180 kilowatts. The reason I fit it with 3 gen sets was mostly because of the reaper power I have on board. Reapers take up a lot of power. You wouldn't really think you would really want 150 reapers, but they take up quite a bit of power, and we also want to be able to like turn off the main engine so we can do maintenance and repair, but we can also go around port. But you can also keep your hotel loads on, and as well keep any containers there that need to be chilled or heated, keep them running. And we also, with the power propulsion on board with the whole shot method, we were able to size propeller. So my ship has a 4-blade propeller with a diameter of 6.5 meters and a 62% efficiency, which is quite high, especially for the type of vessel that I have. So just a little brief touch on the ship's electrical system. So a series of reports were done to complete the electric part of this process. A load listing was first completed to actually identify the electrical components on board, like just anything that you wouldn't think of in the beginning that would need more power. After this, a load analysis was done where we determined the equipment's power and different loads. So we done an emergency condition, in-transit condition, and import condition for this. Once all was said and done, they were separated into 2 different categories, essential and non-essential. So under essential busbar loads, we have 480 volts for 60, 240, 120, 24, and non-essential 480, 450, 440, 240, 120. So the main difference why we had to categorize them is because if you have a blackout per se, you don't want to use any power for loads that you're not going to need in emergency. So really just for like lighting purposes, heating, HVAC, and actually keeping the ship running, instead of like you wouldn't need like your provisions training use at this point in time. So moving on to structure, this part of the project took a great amount of time for calculations and modeling. The structure on this vessel was done in accordance with Lloyd's Registry She's gonna be constructed with mild steel construction, and she's longitudinally framed. And the purpose she's longitudinally framed is being a longer vessel, and especially a container ship, she has a lot of bending moments, hogging and sagging, and even twisting. One thing in particular with container ships, we look at torsion boxes. Now, what we found was there wasn't a lot of research available for torsion boxes, but I was able to implement one at the very top. And torsion boxes aren't used for voids or anything. They're simply just there to counteract any twisting that happens. A slight challenge that I did encounter here with my structure was as you move more on the forward end, as you can see over there, the bow comes in really fast, the curvature comes in really rapidly. So we had to change from longitudinally frame to transversely frame to really counteract and just provide the structure and strength for the curvature up front. Now just a quick look at my capacities. So there we go. So we have a lube oil capacity of 8.7 tons, a sump capacity of 4.5 tons, and our main engine comes equipped with a sump, which is really nice. So we don't have to really stress about where that's going to go, since it probably comes with a sump. We have 9,300 liters of freshwater capacity, or 3.2 tons, and 1.8 tons of black water, 1.5 tons of gray water, and ballast being our biggest at 6,700 tons. So going back to the fuel oil capacity, since she's going to have a 25-day endurance, and being a large ship, she's going to need a fair amount of fuel. But luckily, being on the larger side of the vessels, we have lots of space to put these fuel tanks. So we have a lot of them aft, close to the engine room, mostly day tanks and stuff, but we also have some in the wing tanks. But to do this, we had to put voids in between the sides for pollution regulations and stuff like that. And then moving on to the ballast, we have a large ballast number, 6,700 tons. And this is because we have so many loads being taken off and put on when you're loading and unloading the vessel, and we need to make sure the vessel doesn't capsize or tip over when this happens. So we have lots of ballast tanks all through. We have a huge 4-peak tank as well as an aft-peak tank, and all of our top tanks are all for ballast as well, just to ensure we can fix any trim or heel that happens so she can be stable and avoid slamming. Moving on to the cost estimate, we used indirect and direct methods for the cost estimate, and we went through a bunch of different formulas, and this were the numbers that came in here. So the total initial cost was $49.2 million, and for the output material cost, it was $10.1 million for an estimate. Machinery and plant material cost, $9.9 million. Steel material cost, $8.3 million. Opening labor cost, $6.7 million. Machinery installation cost, $3.8 million. Steel work labor cost, $7.6 million. That's a lot of millions. So the initial cost came out to be $49.2 million, but with the 30% margin that we have to put on, it came out to be $63.2 million cost of estimate for all said and done. And afterwards, we did compare this with Clarkson's, and Clarkson's and similar ships for Sailor analysis. So the average that I found with the 130 ships that I use for my databases, was between $42 to $60 million for a new build cost. And although we're about $3 million over, makes sense with all the stuff that's going on with steel hike prices and everything in the economy right now. And like I said, I left trim stability for last since I had a bit more to talk about it. So for this trim stability, GHS was used to run our load conditions for the project vessel. And for the load conditions, I ran a light ship condition, a port departure condition with voyage and for arrival. And then to expand on these three, for the port departure, mid voyage, and port arrival, I ran each full load of containers, a half load of containers, a full load of empty containers, and then no containers at all. The stability standards that that we used was for the IMO and the Transport Canada regulations. Each condition was first tested without ballast, and then ballast was added to fix any trim or heel on the conditions itself. A challenge I had with my load conditions was dividing the loads equally among the containers on board, and as we know, containers you can hold anything from steel cards to teddy bears, feathers, food, like you don't know what you're gonna have, which is kind of a disadvantage when you're trying to distribute these loads. So what I did, I developed an Excel spreadsheet just to separate my container holds into the 8 container holds that I have, and then for above deck and below deck. Because we had to keep a safe kg to ensure she didn't capsize. So in my below deck holds, that's where you would keep heavier containers and cargo, and then on top you would keep, like as you move up the stacks, lighter loads, so your kg really stays towards like the main deck of the vessel. And then here above, I have a port departure full load condition shown, and this one has ballast added to it. And as you can see, with the help of the ballast and the 4-peak tank, she really sits really nicely in the water and passes all the conditions. Below, I have a mid-voyage condition at half load, and you can see it pretty much sits the same, but as you can see, the only difference really is the fuel tanks. When you're obviously leaving port, you have full tanks of fuel, but then as you get mid-voyage, you're about halfway, so you have to be really careful. Like the captain really has to be like, okay, how much ballast do you need to add on, take off, stuff like that. And yeah, again, ballast is one of the big things that we had to watch out, and I had to keep an eye on the trim stability. But it was a big advantage having so many tanks and so much room to keep as part of the ballast. So when you're unloading and loading in port, you're able to keep stable so she doesn't tip over. So this concludes my container ship project, the 1100 TEU container ship, being constructed for OceanX, which will be sailing from St. John's to Halifax. If anyone has any questions about any topics talked about or anything else in general, feel free to ask. Ashton?
So first off, great presentation. Should the vessel be retrofitted? Because as now, like it's operating to St. John's, so there's no reason to have a self-loading system. But should it be an alternative use where it would need the uploading system? How would you go about retrofitting that on there while also keeping your container capacity?
That would be a challenge simply for the fact where she was developed, where St. John's and Halifax, and both have their cranes and operators there.
Yes.
So to do that, you would probably have to go through a larger retrofit for her, maybe lengthen her a bit so you can actually get space for the large cranes on board. Yes.
Is there a reason why you put your computers on instructors that I think further out computers?
Yes, actually, when I finished it early in the design process, I had my superstructure all the way aft, so there was no room for any containers aft. But I found that to meet my capacity, I needed more containers. But with my superstructure all the way aft, I could add containers without affecting and obstructing my line of sight. So in one of my reference ships, actually the Tropic Hope, she had her superstructure forward and containers aft. So I got the inspiration from that. When I done that, I was able to keep my line of sight regulations in check, but also meet my capacity. Any other questions?
Continuing with unloading, were there any considerations you had to make sure that it would be able to be unloaded in a port?
Since again, she's for OceanX, and OceanX is both ports, like in Halifax and St. John's, they both have their cranes and stuff.
Mm-hmm.
And I made sure they had the cranes, like all the capacities and stuff. There wasn't really much else to look into, so it was already really covered, which was nice.
Very good.
Just a comment, the size is your container size.
Yep.
And it's rated that turning point where it's generally not small, there's a mixed bag, needs self-unloading, not small. So that's it's not uncommon to have the size of it, self-unloading, facilitated in the lowest column.
For sure. And Sean?
Well, If you can see this last statement. The loaded containers, you noted, of course, that you use different loads. You need to put your lower. That is the actual fuel that the vessel loading pattern for
Yeah.
how you load the vessel. Did you modify your valve system to account for how you plan to load your vessel?
I didn't, because I think early on I really took that into account with keeping my ballast really spread out. And again, like as you said, I'll put more heavier cargo up front and below deck as well, because where you have so much weight aft with the engine room, the superstructure, putting heavier cargo up front, below decks will really keep that valve out of, like below the water. You really don't want your focus valve becoming probably tucked out of the water. Now, sometimes it will be, which is all right, but we don't like to see it because that will affect fuel efficiency and stuff.
So,
Okay.
Figure out. Yeah, so. Did you, Skylar, did you give him the thing for the? That needs to go plug in if you want to use that. Good. Change over time? And maybe we can just mute
Something if we have to.
I went through and cleaned everything.
Okay.
Yeah.
See everything. I don't know if it's on.
Yeah, you gotta scroll over to the tapes.
Just turn them on. Now, we still have the stream. Don't have the live stream, check the live stream. You have the live stream?
Up nice and high, Phil.
Yeah.
See if they're getting sound.
Can you just tap your mic? Is it?
Is it on?
Yeah, just turn on.
Check 1, 2. Try now.
There we go.
Perfect.
Yeah, but can you hear them on the live stream? Yeah.
Yeah, I can hear.
Okay, perfect. This one's off.
Its sensitivity is.
It's bad.
I think we're finally getting it figured out.
Just check.
Hello.
Good. So wireless warning, yeah.
Fine, that's what that is, you know.
Just hit the volume button.
Sound reinforcement.
I'll leave this up. Just keep
Yeah,
it on.
it's wireless one.
Yeah.
Which bottom is it, Winston? Which
Yeah,
bottom?
so they're offered these very, so it's either one.
Okay. Thank you.
So it's interesting that these guys are back to back because Skylar is actually continuing her education and becoming a professional mariner. And so we lost one. But we also gained one because Phil was going to become a professional mariner and decided to switch it over to naval architect. Pretty great. And they all cleaned up very nicely. Phil looked nice and very well.
Oh, thank you.
Yeah. These guys have been in survival mode these last few weeks, right? So it's nice to see them kind of clean up and it really looks very handsome. So Philip, are you ready?
I'm ready to go.
Philip Roberts will tell you all about his project.
Yes, thanks for the introduction.
Oh, sorry, 1 second. After Phil is done, we're going to take a lunch break and we're going to come back at what time? Yes. Thanks, yeah. So we're going to reconvene at 1 o'clock and continue on with the presentation. So, go ahead, Phil, all yours.
Awesome. Thanks for the introduction, Winston. Like you said, my name is Philip Roberts. I'm here to present to you my design vessel for Horizon Ales. So first off, a quick little introduction. So the goal of this project for me was to develop a service operations vessel for the offshore market in Nova Scotia. What an offshore service operations vessel is basically one of those offshore ships you see downtown, but instead of for offshore oil and gas, for offshore wind. Intended to assist both the offshore wind industry and the reinvigorated shipbuilding industry that we're seeing in Canada now. And how I'm going to go about this, I'm going to talk to you about the actual design process first. We're going to walk through all the work that actually went into it. Then at the end, I'm basically just going to show off. So let's get to it. So this is just a quick little video to kind of show what these ships do. So in this video, where all the red wind turbines, ones that are either broken down, disabled, or not quite working right, the big ship in the middle is the actual service operations vessel itself. And the two smaller ones are both its daughter craft. So what they'll do is throughout the week, as different turbines fail and come online and offline, they'll all move around and drop off wind farm technicians to these to do the work they need to do and make sure everything keeps up and running. So onto the actual design process itself. Everything all of us ever do always starts with the design spiral. Really what this is the guiding light to how we walk through everything we do here. This is a rough outline of what happens when, what needs to come before what, how we find out our path to actually making a finished ship at the end. And this keeps getting iterated over and over and over, and you know how it goes. You start actually spiraling after a little while. Of course, our design spiral looked a little different than this. So when we started this, we originally did a mission. Oh, I'm caught on something. We originally started with our mission profile, then we moved on to our similar ships analysis, started developing our hull forms and our arrangements, and did our powering and electrical things. I have these combined for a reason we'll get to shortly. We then started designing our structure, and lastly, we did our capacities plan and our stability. Starting off talking about the mission profile a bit. Like I said, this ship is being designed for offshore wind installations in Nova Scotia. And the first real step to designing this ship was just understanding the task at hand and knowing the need that it needed to fulfill. So as I'm sure everyone's aware, Canada's really been moving toward net zero the last few. Most recently, we're really trying to hit that goal by 2050. And the plan is for Atlantic Canada and offshore wind in general to play a big role in how that all comes online. Along with that offshore wind industry, Canada has also been building up its shipbuilding industry again. So we have a really interesting opportunity where we can build Canadian ships for Canadian industries, which kind of builds into the NSS, which originally was intended to go along with mostly government vessels, your military, your Coast Guard, that kind of stuff, pumping government money back into Canadian shipyards to build government vessels. The idea behind this was to kind of build upon that base and look into the more private side of this, taking what we've already started with the shipbuilding strategy and getting, C-SPAN and Irving, making sure we're up online and moving into more private sectors so we can broaden this out into more than just Canada. Just a little bit on the actual wind farm itself. So the one that I'm designing for specifically is by Nova East Wind. This is offshore in Nova Scotia. The wind farm itself is a location called French Bank. It's in between the actual mainland Nova Scotia and Sable Island. The home port that they were looking to build up to be able to construct these wind farms in this home port for the ship was Sheet Harbor, Nova Scotia. And the port where the ship would actually be built is Halifax, of course. Irving Shipyard is right there. If anything ever goes wrong with the ship, it's just a hop, skip, and a jump, and you're ready to get her fixed. So from the mission profile, a couple really important things that I wanted to keep in mind for this whole project was the ship really wanted it to be built in Canada, really wanted to maintain comfort and livability for the crew who are going to have to work and play while all on board the ship. Since we're using this for wind turbines, we really wanted to look into green shipping methods because it doesn't look good on your nice wind farm posters, that big puffs of black smoke coming out from your ship. We needed some kind of cargo handling ability and methods of crew transfer, of course, because ship's not much good if we have no way to actually get the equipment and the people onto the turbines.
And we needed to meet endurance requirements for missions. We don't want this ship having to go back and forth every week to restock or change people. We need to be able to keep out for that long. So a first step for actually designing this ship was state-of-the-art analysis. This involved gathering a bunch of similar ships built in the last decade, which was easy for this because all the ships in this ship type have basically been built in the last decade. Gathering those, compiling a bunch of data, and making useful graphs that we could turn into actual data to design the hulls on. This example right here is for our my length overall versus deadweight scale. This was used to actually find the cargo capacity, which went with around 2,500 tons. A few designs from that SOTA analysis stood out. That's a great looking ship, by the way. And you'll notice it's really similar to mine because I liked it a lot. Ships like the Edda Breeze or the Grampian Durant, which are based on salt ship designs and barge ship designs, really influenced the project for me. Both of these ships represented proper, focused service operation vessels. For a long time, this industry draws straight from the traditional offshore oil and gas industry, and these are two good examples of them actually building purpose-built ships for the job. After the SOTA, we went into the hull form developments, which was all about turning the values we got from that SOTA analysis into an actual boat. As a couple of the guys explained before, we basically started with half cylinders, been chiseled away as we went to create something a bit more ship-shaped. Big thing for this ship was creating an efficient hull that could still house everything. This is a really tight packed ship. There's a lot of equipment, there's a lot of crew, there's a lot of things that just need to fit inside of there. But we don't want to wind up with just a barge with a big box on top of it. We also don't want to wind up with a box on top of it because, well, why not make a ship that looks good too? You saw the competition we had on the corner. We make a barge with a box on it. You know, it's not going to look very good on our brochures. Then we went on to rearrangement. A couple of the important things here were creating layouts that make sense and make good use of the space. Again, it's a really tight packed ship, making sure the layout makes sense. Everything's in a place where it's easily accessible and useful. And one of the major things for this was developing a bridge with lots of good visibility. There's a lot of different work happening up on that bridge, a lot of sight lines that you need to take into account to make sure when you're piloting from any of the stations, you can see everything. Power and electrical was what came next, and these are together for an important reason. Like most of the rest of us in our class, I think all of us did haul, chop, and minen. And haul, chop, and minen is great, especially for shafted ships, because it'll calculate your required propulsion power to push the ship from the water. The problem is with a diesel electric cell, you have to go more in depth to actually find out the other numbers you would need for, you know, your hotel loads, your crew loads, because that's all running on your main generator. You don't have extra generators. Everything's running off the same system. We were also looking at environmental considerations, checking out different alternative fuel sources. One of the big things with these wind turbines is they're trying to make clean hydrogen with them. So one of the other things looked at for this ship was using dual-fuel ammonia engines. As well were battery systems, such as the Corvus Orca system, which did wind up on this ship because you wind up with huge savings in fuel, especially in your maneuvering modes, and just, it's good.
Fair.
Other requirements. The bane of my existence in this project was dynamic positioning, your DP. This is the whole single line diagram. You notice there are a lot of bars going on here. There's a lot of stuff. So what DP is, it's a redundancy requirement. So all of this ship type in particular has a DP2 requirement. That means any active component in the system needs to be able to go down, and you need to be able to maintain position wherever you are. That means your thrusters, your azimuth pods, main generators, any of those go down, you need to be able to maintain position. This is hard because there's a lot of mission critical equipment. So it takes a lot of digging. And yeah, just to reiterate, redundancy. I'm going to sound redundant from saying redundancy so many times in this presentation. Structure is what came next. This one gave me a lot of problems because I had, originally the way I had my deck set, I didn't have enough space under my cargo areas, and the decks had to move, so a lot of structure things changed, and it was just a tangle. But some of the things that were really important with this was making sure the structure could resist the forces, because we have some heavy loaded decks like the warehouse and the working deck. Also maintaining structural continuity and keeping that adequate space. Again, lots of stuff in a small ship. You gotta make sure you have room. Capacities and stability. A ship like this has a very wide range of operational profiles. It's a one size fits all kind of ship. So making sure the ballast requirements could be met for a lot of different loading conditions, and that you could fit the ship to fit the need was really important. Making sure that we could also pass the extra requirements, because this did need to meet the offshore ship requirements for stability. Our worst condition wound up being was mid-voyage with ice accretion, with cargo operations, and with cargo in the warehouse and on the working deck. I'm not saying that 10 times fast because I can't. Yeah, that's all on the process. Now on to the actual fun part of the ship itself. So what we came up with to meet the goal of this. This is the Horizon Aeolus. She is 88 meter long, 19.5 meter wide, 6,500 ton displacement ship designed to meet all the needs of this offshore installation. A couple unique design features right away you'll notice. On the aft end, she has this very nice rounded cruiser stern. Also a very deep V, if anyone ever liked speedboats or that sort of thing. That's to help with directional stability and also to help with wave breaking as the ship is backing up towards the wind turbines. The other big one you'll see is the big post right in the middle. That is a motion compensated gangway. That's how you actually get the crew onto the wind turbines. So as you're out there, that arm will twist and it moves with the waves. As you put it out, everyone can walk right across and can get on. That's our main mode of transferring crew to the turbine. Like we just talked about, the motion compensated gangway and the cruiser stern. There's also a 5-ton deck crane that's used to help transfer cargo. The gangway itself can also operate as a lightweight crane for up to about 1.5 tons. The crane and the gangway are both good up to 3 meter seas. Nova Scotia, I remember looking at the weather things, that works out to approximately 260 days out of the year where you can be up and operating with both of those things. So our uptime on this is really good. One other important thing, there is a crew transfer vessel docking station on the port side. So crew transfer vessels are smaller ships meant basically day boats for the wind farm. So it can come up alongside and it's on the side with the crane, so you can move your cargo on and off of it easily. A couple other features to go along with those DP requirements. So we have 2 bow thruster and 2 stern azipods. These were both sized to meet requirements so that either piece in the system can fail and it can still maintain position. The pods are ABB DZ980s, producing 1,700 kilowatts apiece. And the bow thrusters are both steer props and they do 1,500 kilowatts each. For the power setup, we're using 3 Wärtsilä L25s. After some looking, I realized I don't know as much as I'd like to know about engines. So as I was looking at the DP, the dual fuel requirements, and trying to make that work, it didn't really work out, so I decided to go with the tried and true MDO powered diesel. What did still make it in was a Corvus Orca battery system. That's a 686 kilowatt battery. It's not intended as its own power source, so it doesn't really have a fully electric mode. It's mostly in there for the savings you see in the new modes. That battery is there to pick up the slack when the generators are missing out. Wärtsilä did a few studies on it, and they're seeing anywhere from 15 to 20% improvements in fuel economy with this type of system in there, which is huge. On to some of the layout features, one of the big things I was striving for was to get single cabins for the entire crew. So we have 80 actual crew members on board. That's ship's crew and technicians included. It's a lot of people to fit in. And the big thing with crew comfort and making the ship nice is not only do we have to compete with other shipping companies, we have to compete with onshore wind farm installations. One of the reasons these ships wind up being so nice inside is because, you know, when you have to compete with an onshore installation and everyone gets to go home every day to nice and comfortable things, kick up and watch TV, you need to be able to compete with that and say, hey, this is still something worth doing. You don't have to live in a broom closet. And so along with that, we also have some very large common areas, a lot of places just for people to be people and hang out after work. Another thing that I was really focused on was making sure there were large internal and external cargo areas. So we have approximately 400 meters squared on the working deck and a 300 meters squared warehouse on the deck below. As for the machinery arrangement, again, lots and lots of stuff in a tight, compact area. This is just a glimpse of some of the machinery that has to go down there. You can see the main generator sets up there. You can see the marine sanitation device and the bow thrusters. But yeah, making sure everything is easily accessible and can be worked on, which the diesel electric system definitely helps with that because it just offers you a lot of extra flexibility with placing things in places where you can. With shafts, you're limited because you have to run the shaft. Some other features, talking a bit of a bridge layout. So there's multiple actual conning stations, of course. The main transit one, of course, is up forward. That's got a nice setup, ergonomically set up, so whoever's piloting it can reach all the controls in one place. There's also separate conning stations on both bridge wings and one aft. And so no matter the work situation, you always have a conning station and you can see what work that's going on. In this picture on the bottom here, you can see a desk with a few monitors on it. That's the actual control system for the gangway. Somebody actually runs that. He sits down and it's in a place so he can look over his shoulder and see what's happening. Some of the structure features. So this is primarily transversely framed, except on the working deck where we switched to longitudinal framing for the added strength on this. This was all classed using Lloyd's. Again, this model, I get it. It's a little rough. Again, having to move those decks really put this one a little behind. This is one of the things I definitely look back and improve upon looking back. The actual capacities themselves, so like we said, making sure that there are a good range of ballast tanks to be able to adapt to different loading conditions, types of things going on, so that no matter where the cargo is or what we're doing, we can keep the ship at a good place for both working on and for actual hull efficiency itself. Fuel tanks and freshwater tanks were designed to be as close to the longitudinal center of flotation as possible, so that as they empty and fill, you're not affecting the trim and list so much. And the fuel tanks themselves were sized on, of course, actual manufacturer data. We had fuel burn, which carries about 570 cubes of MDO, around 480 cubes of freshwater, and approximately 1,600 cubes of ballast. So realistically, we're a light carrier. Again, just to talk about a few improvements, DP system checks for sure. If anyone came up to me during the open house, you'll notice I was saying it should be close to meeting DP requirements. All of the propulsion system itself and all of the electrical stuff looked at has all been split up and divided to make sure that the things that we do know, but it's a very complicated system. There's a lot of moving parts in it. So double check to make sure all the mission critical equipment is properly split is important. Engine room and just lower deck heights in general. As I said, I had to move one deck and that really set me back. So going back and reworking some of those from the start and getting everything laid out in a way that makes sense would help a lot. Again, fixing the structural layout, again, because it got a little set behind, so it definitely needs some work. And something the guys from Robert Allen brought up yesterday, anti-heel tank sizing. So this ship does have an anti-heel tank on it. It's currently 150 cubic meters. So looking at extending that out so it can have a greater effect on actually reducing the roll of the ship would be another thing I would glance at and double check. The very last thing we did for cost methods, these were done using Carriot as well as similar ships. This worked out to a total cost per ship of around 89 million Canadian dollars. Compared to some other ships like Febreze and the Grampian time we showed up, those are in below 90 millions. So we're within reason. One thing to keep in mind is because this is being built at Irving and they haven't built one of these ships before, there could be a little overrun there, but this is a good first estimate. And from there, are there any questions? Winston, that shot up right away.
They're great presentation.
Thank you.
Absolutely, loved it. What I wanted to know is, at the start of when we were first proposing this particular vessel type, what kind of topics or sources did you look into to find out more information about this?
Well, the first place I went was straight to Nova East Wind, and I was kind of surprised when they got back to me. They gave me some good insights into kind of the job they had going on. Not much of us made it into this because I wasn't sure if I was allowed to share a whole lot, unfortunately. But that was the first place I went, just trying to figure out more about what their plan was and how they wanted to go about that, because that would help me drive the design of this to better meet those needs. Ashton.
Yeah, like Winston said, great presentation. Really impressive render too with the boat going up to the wind farm.
Thank you.
2 questions. So your DP2, is there any reason why you're not DP3 for the extra redundancy?
It's not required.
Okay, it's just for the
That's the answer.
Yeah, that's okay.
It's under DN. Well, it's the higher risk situations your ship is in, the higher DP class you need usually. So usually when you start getting into DP3, you're working with hazardous materials or ROVs and expensive stuff. DP2 for this made sense, and that's what DNB required for.
Gotcha. Yeah. And my second question, for the vessels, like more often than not, like at sea, would you have a sort of vessel come up and actually give you fuel or other provisions, or would you have to just go in port?
At sea provisions transfers, I didn't look at. You could, like if you send out one of those crew transfer vessels and load some food and that sort of stuff, you wouldn't be able to do anything big with a crew transfer vessel, but yes, the main design idea was that it would go back to shore every month and refuel and get ready for the next trip. Yeah. Sean.
Well, so what you're experiencing as the architect is your first time through the spiral, you're seeing a lot of things where you're kind of, well, shoot.
Yeah.
That's the whole point of that spiral, right?
Yeah.
So that's completely expected, certainly inside of something where you have a unique design and a sort of field area service. So don't be discouraged by the things you kind of bumped into.
Yeah.
Realize, oh, I gotta do that again.
Yeah.
Those things happen. Safety deck heights, very common.
Yeah.
So keep with that. The piece of that curiosity on is your cargo deck requirements. Lloyd's, well, most of the class societies do carry with them calculations required for actual loading on the cargo decks.
It is.
That would actually drove some of your structural change.
That is exactly what drove a structure change. Originally, we hadn't noticed that, but when we went back through and we realized there was a separate calculation when your deck loading gets so high. So this ship has a deck loading of 2.5 tons per meter squared for the working deck and for the warehouse deck. And going from the original formulas, which didn't have that included, to the ones that did have it included, you went from, I think it was, trying to think in millimeters how tall a millimeter is now. You go from structure this tall to structure that tall. But originally I had all my decks set at 2.5 meters because I was like, oh, well, this makes everything nice and simple because everything's the same. And yeah, once half of that's taken up by structure, it just doesn't quite work out. Yeah. Thank you.
Back to your dual fuel. So you landed on MDO.
Just with MDO.
What was, I'm just curious, what was your results of that search?
It was, so the reason we went with L25 for the main jet was because they had an MDO version and a dual fuel version, so we could compare apples to apples. The ammonia version, actually, wait, sorry, could you say the question one more time so I make sure I'm answering the right thing?
No, you did research, I just want to hear a little more about that.
Oh.
Going back.
Yeah, so.
Side, I'm on the other, but
Well, the main thing that made me swap away from ammonia was just the complexity of trying to get it to work and trying to work out different operating conditions for just so many conditions you'd have to look at. The main difference with the ammonia versus straight diesel for this was the capacity. Ammonia is far less energy dense than diesel. I think it wasn't quite double, but it was around double the volume of MDO you would need for the ammonia to make up for that. And there is space in the arrangement to get that tank. Yeah, but it does, yeah.
So, but what about, actual access to that consideration? Where can you get?
Yeah, well, that's where the wind farms actually producing. So that's one of their big selling points was they wanted to produce the green ammonia and sell it to Germany. And it's, well, if the ammonia is already there, can we go and look at that? Because while that's getting set up, those engines can still run on just MDO in the meantime.
And this is getting off topic of ammonia. So that's produced where? Physically where they.
I'd have to double check that. It's been a while since I should have read up on the ammonia stuff before I did this. Yeah.
You mentioned earlier on one of the factors, the environmental side of it.
Yeah.
And our greener option. There's a whole idea of, certainly.
Yeah.
And I will know the bias towards recovery that was obvious, but.
But there is a reason for it.
Yeah.
Well done.
Thank you.
Love your suit, by the way.
Oh, thanks. Should have had the shades. It would have been a perfect walk off.
There you go.
Any others? All right. Thanks, everyone.
All right, guys, that concludes our morning presentations. We'll reconvene at 1 o'clock after some lunch and continue with,
Yeah.
so guys.
Done. Make her kick back and relax.
That's right. Another time.
Yeah.
So I probably won't be back for a month.
Switches at the top.
Deep breath skill.
Oh, that works.
I don't know, this chair is.
I don't have So I look Sorry, my hand. Yeah, I just need to. Wait, so was there a clicker around?
Is it, do you have the,
I can just use a mouse. No, no big deal. No worries.
do you have the dongle for it?
Yeah.
You got to get in.
I
plug it in.
have controller.
Yeah, just plug it in. Yeah.
What is it?
So, which way is it?
Press down and go.
Which way is it?
Yes.
Sorry, yeah.
Welcome back, ladies and gentlemen. With some delay a little, so I'll just figure it out. Up next, we start our afternoon session. First, we have Kayla Scott. I'll let her introduce her project. So, Joy.
Hey, okay, there we go. Okay, so hi guys, like Ian said, my name is Kayla, and this is my project. It's an 84-meter Canadian Coast Guard buoy tender. Okay, so to give you a brief overview about what we'll be talking today, I'll start with an introduction, which includes the mission profile, the types of buoys used on the vessel, and the area of operations, followed by the SOTA analysis, the lines plan development, general arrangement, powering requirements, electrical analysis, followed by the structural arrangement, capacity plan, stability and trim, cost estimates, the design changes, and of course, my final thoughts. So to begin, the introduction. In 2020, the Canadian Coast Guard implemented 4-season navigational buoys in the St. Lawrence River between Quebec City and Montreal. A larger, more advanced vessel is required to transport, install, and maintain these buoys to ensure year-round navigational safety. Thus, my mission profile. So with this in mind, I designed my project vessel, the Canadian Coast Guard ship Finnegan Leopold, to support this new buoy initiative. Its main goal is to deploy, maintain, repair, and replace navigational buoys and beacons, with the secondary duties include assisting with the marine emergency response operations and supporting any surveys and marine inspections. As for the type of buoys being used on this vessel, there were 2 new 4-season navigational buoys designed specifically to be deployed in the St. Lawrence River to withstand the severe ice and weather conditions in that area. There are up to over 184 new buoys to be deployed in the river between Quebec City and Montreal. These newly developed designs will need to be replaced once every 2 to 4 years rather than every 6 to 8 months. So this is just an example of those 4-season navigational buoys that will be used on my ship. The first one there is a 1.3 meter model, as well as a 0.7 model. And these various sizes are intended for the different water depths that are within the river itself. As well, there's going to be more types of buoys that I'll be carrying on my ship. The first one being a mooring buoy, and that's used to provide a secure anchorage point for the vessels, so it eliminates the need to drop anchor. I'll also be carrying any data buoys, which will help with the marine research, the environmental monitoring, and the maritime safety. So let's talk about the area of operation. This vessel will be built in Halifax, Nova Scotia. This will also be its home port. It will make regular stops in Quebec City, as well as Montreal. It's operating, like I said before, in the St. Lawrence River and the Atlantic Ocean. This vessel will have an ice-strengthened hull because of this, because there's tons of ice there. So now, with all the introductions done, this is where the real fun begins. The first step in the process was figuring out our principal particulars. This was done by completing a state-of-the-art analysis using similar ships, so the SOTA analysis. I was given a known dead weight of 1,700 tons, and this is what became my starting point. For my vessel, I used a total of 68 similar ships, with only 5 of those being Canadian Coast Guard. Canadian Coast Guard buoy tenders have a significantly higher dead weight and longer length than a typical buoy tender. So as an example, this would be an overall graph of my dead weight versus length graph. So this was the first graph that I found. I noticed that when I was first comparing specifically Coast Guard buoy tender vessels to other regular buoy tender vessels, the dead weight to the non-Coast Guard vessels had a much smaller dead weight, which in turn meant that they had a shorter length. Therefore, it was decided that when I was comparing similar ships, I focused more on the Canadian Coast Guard vessels that I gathered, since that's the ship I wanted to be. So as you can see that clump down there, that's the regular buoy tenders. But I wanted to be Canadian Coast Guard. So that's where the X is. That's where I gathered my lengths. So we did more analysis, and that's how I gathered my principal particulars. These were all based off the SOTA analysis. So my length overall is 84 meters. My length on the waterline is 81.5. My breadth is 16 meters. I have a draft of 5.5 meters. My depth is 7.6. I have a displacement of 4,411 tons. My max speed is 15 knots, and I have a cruising speed of 13 knots. My number of crew is 26, which means I have 8 officers and 18 crew. I have a range of 5,500 nautical miles, and my endurance is 60 days. These particulars became the foundation of my ship's design. Next is the lines plan development. So here's an example of my lines plan, where you can see that the lines and the shape of my vessel. The vessel will feature a displacement monohull, which is a commonly used hull type. This vessel will be designed with a conventional bow and a transom stern. And these are my lines plans. So there were no parent lines used, so I started with a cylinder and shaped it to how similar ships looked. Another thing to note is that I did not choose a bulbous bow, as I'm spending the majority of my time at a lower speed, so there will be no advantage of having a bulb. Since the vessel is also intended to operate in ice conditions, a bulb could increase the risk of structural damage. In other words, I didn't really want to beat the nose off of her, so I kept it pretty straightforward. When comparing with other Coast Guard vessels doing similar missions, they also didn't have a bulb, so that really confirmed my decision. And this aligns with my mission profile and, of course, similar ships. On to my general arrangement. So I didn't have many examples to go by for my general arrangement, since most of that Coast Guard information is confidential. I used what little information I did have and the things I've learned throughout this program to design an arrangement that was efficient for the vessel's mission and made the most sense. So to kind of go into more detail about it, this is the profile view of my ship. It's the centerline elevation view. Some notable things on this would be the bow thruster that's installed on the vessel to improve the maneuverability. This is important for buoy tending operations because we want to be able to place the buoys and how we're going to lift them. It also outlines the cranes and the engines, but more on that to come. So here we are, the more yet to come. This is my main deck. Some notable features on this is my 25.6 ton crane and 2 6.8 ton cranes. These cranes will help lift the buoys into the water. There are also 2 hatches so that the buoys can be stored in the cargo holds below. This is also space on the deck to store those buoys. Along with the 2 lifeboats, there's also a fast rescue craft, and the FRC is placed on the main deck as part of my secondary duties of being a Coast Guard vessel for search and rescue missions. So for my tween deck, this is my tween deck, and some notable design choices include the engine control room and the machinery spaces, but it's also where the majority of the buoys will be stored. The vessel has a small steering compartment space, and so I chose a rotary vane steering gear as it has a small and compact design. This is similar to other Coast Guard vessels. And for the tank top, this is most importantly where the engine room will be. It has 2 6L20 and 1 9L20 Wärtsilä diesel engines. It also has a marine sewage treatment plant, a pump room, engine stores, propulsion motors that also use the variable frequency drives to help operate those. And this vessel will be fitted with 2 4-blade controllable pitch propellers. As for the upper deck, this will feature the galley and separate messes for both the crew and the officers. Because we're a Coast Guard ship, they like to keep that separate. And of course, all the food storage. Next to it would be the forecastle deck, and this has a provision hatch and a crane for easy access to all those food storage to load those provisions. This deck also houses the crew accommodations and a crew lounge and a gym. On your left, the A deck features accommodations for the officers, an officer's lounge and a meeting room. And to the right, that's the bridge deck. The bridge has a 360 view of the water ahead, which is important for its line of sight. As well, it also has a view of the working deck behind it, so we can see the boys working with the boys. So the vessel will be equipped with modern navigational technology. And it also has a chart table or two, so that's good.
Yeah.
Next would be the powering requirements. So this vessel will have a diesel-electric configuration. This will allow for an efficient power distribution, which is beneficial for a buoy tender, as it will be operating in a variety of different modes. For example, transiting, buoy laying, maneuvering, standby, harbor mode, etc. Another reason why I chose diesel-electric was because a lot of the similar vessels in the Canadian Coast Guard fleet are diesel-electric, so it just seemed like a logical choice for me. Like the rest of my class, I used the Hull Trap and Mena method to figure out how much power I would need. The vessel will be powered by 3 engines, one Wärtsilä 9L20 and the 2 6L20s, with redundancy ensured by that third engine. This means it can run at the required power needed at full speed with only the 2 engines. The 3 engines will generate a total of 4620 kilowatts, but at the full speed needed, the vessel only requires 3300, so I meet that, and that's good. It will also have the 2 electric propulsion motors that will be installed, each of it delivering the 2000 kilowatts and fitted with a reduction gearbox. Furthermore, we had to do an electrical analysis. This is a critical component to ensure that the electrical system of the vessel is designed to meet the power requirements efficiently and safely. This process involves identifying and categorizing all the electrical loads on the vessel. The largest factors for me to consider were the bow thruster and my propulsion motors. So data from similar vessels were used to estimate the expected loads on the design vessel. The 3 primary load conditions analyzed were in transit, in port, and emergency mode. The highest mode was the in transit mode, which had a peak load of 4193 kilowatts, which I meet as stated previously with my 3 diesel engines. By using this data, an emergency generator was selected to provide power in case of main generator failure. So this vessel is equipped with a Caterpillar C18 marine generator that's rated at 565 kilowatts, which sufficiently covers the emergency power requirement of 343 kilowatts, and that ensures it's compliant with the safety and regulatory standards. This generator is also located on my main deck, so it's above the main wire line, so in case of any emergencies, it's still good to go. Along with the electrical analysis, we had to do a single line diagram, and this is just an overview of the vessel's electrical distribution system. It's separated into 2 different flows, the essential and the non-essential. This design ensures that if one section fails, the other one remains operational in case of emergency. Next was my structural arrangement. So for this vessel, I followed the rules and standards by Lloyd's Register, which will ensure that it meets all the required safety and construction guidelines. In addition to Lloyd's Register, the design also complies with both the Canadian and international maritime regulations. As previously stated, the vessel will be ice strengthened. Specifically, the vessel will be designed to an ice class 1A standards, which means that it's capable of navigating up through the ice of up to 1 meter thick. The material used to build this vessel will be a marine grade steel, and the vessel has 5 watertight compartments, or watertight bulkheads. Next, the primary framing system used will be a transverse framing. However, on the working or the main deck, I incorporated a longitudinal framing system because I thought that I needed to do something more difficult. And this is to better support the operational loads in the area. So for the transverse framing, the transverse structure of the vessel, this will have a frame spacing of 500 millimeters with a web frame placed at every 3rd or 4th frame to provide additional strength and support. And in the longitudinal direction, the frame spacing will also be 600 millimeters with a web frame included at every 3rd or 4th frame, depending on the location space, to maintain structural integrity. Furthermore, this is my profile on decks. This is a close-up of the main deck on the structural drawing. And here you can see the longitudinal framing, which is an essential structural component to the vessel. Furthermore, so next would be my capacity plan. Tank capacities are a fundamental part of the vessel design as they determine how and where to store essential materials like fuel, fresh water, ballast, lube oil, and cargo. Designing these tanks require careful consideration of the ship's total internal volume and how that space is divided between machinery, accommodations, and storage needs. These decisions need to happen early in the design process to ensure that each system has adequate capacity for the vessel's operational requirements. This was especially important in my design due to the small size of my vessel. With the limited space to work with, I had to be more strategic on how I arranged my tanks to ensure that the functionality was still there without compromising on the space needed for the other systems. So that was a fun and interesting challenge. This table outlines the minimum total volume of each of the tanks. My vessel exceeds these volumes, and I determined these numbers based on a crew of 26, a range of 555 nautical miles, and an endurance of 60 days, and of course, along with my similar ships. So here are my tank capacity plans. As you can see, most of the tanks are located in the double bottom because it's the most efficient use of space. Placing ballast low in the ship improves the stability, and therefore it made the most sense to position these tanks below the tank top, and that's it there. As for my stability and trim, I ran a total of 23 conditions through DHS to evaluate the vessel's stability throughout its operations. For port departure, mid-voyage, and port arrival, I analyzed full, half, and empty cargo states. As well, at port arrival, I also assessed the impact of operating the working cranes in combination with the different cargo and ballast configurations. Each condition was tested both with and without ballast. And in addition to the standard loading conditions, the vessel was also tested in light ship and light operating states to ensure the safe performance under minimal load scenarios. The worst case condition for this vessel occurred while operating in ice with ballast on board, carrying half the cargo and actively using the working cranes. So it was kind of a unique condition for that. This combination produced the most demanding stability scenario in the analysis. My vessel passed all of its conditions. However, there is a slight forward trim happening in a few of those conditions, and this would be a good opportunity to reevaluate it if there was another turn on the design spiral available. And by slight trim, I mean 1 degree. If I had the opportunity, I would like to figure out a way to make it a more even keel. As for the cost estimates, I used Carriette's method to estimate the vessel's construction cost, which gave us a figure of $45.5 million US dollars, or about 63.7 million Canadian. This was helpful for early estimates, but this method is a bit outdated and likely underestimates current costs, especially considering post-COVID inflation and the rising material and labor expenses. To get a more accurate number, I compared it to similar buoy tending vessels built in the last 4 years, which averaged around 68 million US dollars, or 95.2 million Canadian. This aligns better with the new Coast Guard builds. Based on this comparison and the industry trends, I rounded the estimated cost to 68 million US dollars, or 95.2 Canadian, to stay consistent with the current standards in North America. So one design change I would like to make is to increase the fullness of the aft section of the vessel. This adjustment would create more space in the steering gear flat, which will allow for easier equipment placement and a better accommodation of the rudder slide. I made a small modification to this at the beginning of the spring term, but due to time constraints, I was limited to how much I could adjust due to the overall shape. And that was a fun weekend, so. Another change I'd like to make is to redesign the cargo holds to be symmetrical. Right now, both the openings and the holds are located on the port side, which made it tricky to keep the vessel balanced during the stability testing. So if I had my time back, I would make it more symmetrical. As for final thoughts, there are definitely a few things I'd change if I have more time, but overall, I'm confident that the Canadian Coast Guard Finnegan Leopold is well designed for the initiative. It meets the key requirements, performs safely under tested conditions, and is ready to operate efficiently and effectively in the intended environment. It's hard to condense into 20 minutes all the work that we've done over the last year. Although challenging, I found this experience rewarding, and I'm excited for my future in shipbuilding, wherever that takes me. With that being said, I'd like to thank my instructors for allowing all of my questions because we know I had a lot of questions. And for that, I want to give you guys some props. So thank you for your time. If you have any questions. Yes, Winston.
Excellent job.
Thank you.
For your variety of different boys, are they all outfitted with GPS location systems that can be retrieved at later dates and monitored?
Yes. Short and simple, yes. Yes, they are, yeah.
Yeah, like Winston said, great job. Is it pronounced boy or buoy?
You know what? That's a great question that we had a debate on, particularly me and Ian. It's boy or buoy, depending on where you're from in the world. I tend to say boy.
So final remarks, the vessel was designed for the boys.
The vessel was definitely designed not for the boys, but by a girl. So.
There you go.
Yes, in the back. I didn't answer that, did I? What a great question. So I chose a boy tender because this past summer I was lucky enough to work on a refit of a Canadian Coast Guard vessel. And so I thought that a Canadian Coast Guard vessel would be an interesting project design. Plus, like, it gave me an edge because I already saw one in person. Furthermore, like, it's a work ship, so I thought that these would be vessels that I want to work on in the future. So why not get a head start here? So that's pretty much. So many. Okay, Mark. Hello.
Sorry, I
I didn't apologize though, Mark. Not this time. So.
You worked for last summer, you worked for Coast Guard vessels. Fine, we got good experience, a lot of things you took from that.
Yeah, like just even seeing like in person, like because I couldn't really get my hands on any kind of plans, I got at least the memories of it, so I could figure out like how big things were in person and like get a feel for the ship size itself, so I could like refer back to that knowledge and put it in place here. So real hands-on experience was good to have. Cool.
Good job.
Thank you. And John?
Sorry, you can't ask questions.
You mentioned earlier in the beginning of your presentation that the Coast Guard vessels tend to be over salts.
Yes.
Did you come across as to why that was?
Well, the ones that I was looking at, those 5 that I particularly had, they were mostly icebreakers. And so I think that was why that they were a little bit bigger than the other ones, because they had that extra build to them. So that's what I'm surmising. Sean, hello. Sorry, Ian. Okay.
No, it's a very you see all the purposes. Question for you regarding longevity. Was there a lifespan as part of your assessment on the design life for the vessel? Coast Guard's maintenance for running your vessels 20 to 30 years.
That's totally fair. I actually didn't run any kind of longevity test to it, but where it is Coast Guard, I'm hoping that it would be around for the next 30 or 40 years. So I'd say that it is.
It's an interesting piece of our design as far as understanding the operational life that our clients are.
Right.
Coast Guard, you tend to add X percentage on top of that. But they do maintain their business very, very well. That's not all very well. But it's a very interesting piece of design.
Cool. No, thank you. Yes. Hi.
Kind of bouncing off Sean, so of course they want your vessels to have a longer life cycle.
Yeah.
One thing that's working against them, of course, is corrosion. Did you have a chance to look at any corrosion mitigation systems or coating?
We did like a brief analysis of that in like the electrical analysis course. We did like an impressed current system, but other than that, we didn't really dive too far deep into it. So maybe on the next turn of the spiral, that would be something to look at. Yeah. Thanks. Is there anything else, Ian? Oh yeah, one last question. Yes.
There you go.
Yeah, okay, good question. Actually, it's named after my cat, so very important person. Thank you. Good? Cool.
Back to the Coast Guard vessel lasting a long time, it has 9 lives.
Yeah,
Yeah.
perfect.
Yeah, props. That was great. There you go. Oh, sorry.
I'll get out of your way.
Oh, no.
No, I think I finally have everything.
Yeah, props.
Just not even gonna move, just gonna.
Yeah, they're going to. Yeah. I don't know what
Well, that's
awesome.
No.
Oh, she probably did.
Well, you just.
Yeah, just down here. Yeah.
Oh, there's that. Oh.
Yeah. Let's see now.
Ladies and gentlemen, thank you, Kayla. Up next, we have Fred Calloway, one of the marine mechanical design students. Project.
Thank you very much. Good afternoon, everyone. Thank you. As Spirit just said, my name is Fred Calloway, and I'm a third-year Marine Engineering Systems Design student. Today, I will be presenting on alternative marine vessel cooling solutions. Now, for a quick overview, I'll be going through a brief introduction, talking about my project vessel, why I chose the one I did, and some of the constraints or challenges I faced in designing the machinery spaces of this vessel. Next, I'll be going over some of the cooling options that I went over for trying to solve these problems, namely central cooling, keel coolers, and box coolers. Then I will do a brief conclusion covering the decisions I made and why. Next up, quick introduction. When selecting my project vessel, I wanted it to be something I was personally interested in. And I guess my biggest exposure to ships in general growing up was my grandfather. He was is a master mariner for a good number of years and captained a tug and barge service for a long while. He's had many vessels, but the one I keep thinking about whenever I think of him at the wheel of a tugboat was this one, the Point Vim. Now, the Point Vim was a 30-meter long ocean-going tug, and as far as I know, it's still in service today. Now, So it seemed only right that I chose an ocean-going tug as well. Now, my project vessel is a 40-meter ocean-going tug. It has a breadth of 12 meters, depth of 6 meters, draft of 4.6 meters, takes a crew of 6, has a total installed power of 6,180 kilowatts, has a rated bollard pull of 40 tons and a gross tonnage of 950 tons. Now, diving into the heart of my project vessel, the machinery space and engine room. This is a very simple profile view of my machinery space. Swinging around to a plan view and giving a better idea. Maybe. Okay. Now, a plan view of my engine room and machinery spaces. This is my, first of all, this is my machinery space as it currently is, equipped with all the different pieces, items, and equipment that I have spec'd for it. And one of the biggest challenges I faced with designing this engine room was space, or lack thereof. The biggest issue I ran into at first was my cooling system. After going through the various calculations needed to cool simply my main engines, this is how much space the traditional plate-style heat exchangers would have taken up in my engine room. As you can see, that's quite a lot of space dedicated to just cooling the main engines, not gensets, gearboxes, hydraulics, just the main engines. So it was at this time I had to look into other options. Which brings me to the next part of my presentation, the various cooling options that I explored. First of all, what does a cooling system do? Cooling systems maintain any equipment on board at an optimal operating temperature. Some of the common items handled by your cooling systems include your propulsion engines, your generators, your gearboxes, any large electric motors, HVAC systems, or hydraulic systems. This is not an all-inclusive list. There are other items as well. This is just the big ticket items, I'll say. Now then, the first option, and the one that we were sort of guided towards in our program, was central cooling with making use of a gasketed plate-style heat exchanger. A gasketed plate-style heat exchanger specifically uses a closed-loop system which pumps freshwater and additives through the engine, which is then cooled by seawater using a fluid-to-fluid heat exchanger. These typically combine the high-temperature and low-temperature circuits for your cooling, for your propulsion engines into one or two main heat exchangers. Now, as for some advantages of this type of system, you can adjust your freshwater loop with corrosion inhibitors or antifreeze as needed. Because of this, there is little to no corrosion on your freshwater side of the loop. And because your heat exchanger is inside the vessel, this makes maintenance and cleaning generally much easier compared to some of its alternatives. As for the disadvantages, there is still potential for fouling on the seawater side of your loop. There is a more complex initial installation, and as your heat exchanger is inside your machinery space, there is the possibility that it will just leach heat into your machinery space, warming it up significantly. Now, for a general overview of how a plate heat exchanger works, I've prepared a couple slides. Now, a plate heat exchanger works using a closed freshwater loop and an open seawater loop. The closed freshwater loop circulates the fresh water heated by the engine into the plate exchanger, as you can see in the red plates here. Now, the open seawater loop will then pump seawater from the engine into adjacent plates, or rather into the adjacent pockets between plates, as you can see in the blue. Now, due to just the thin plates separating the hot and cold water, this allows heat to leach from your freshwater loop into the seawater loop, thus providing continuous cool water for your engines. Now, as an example image, This is a plate heat exchanger as you would see it hooked up. One thing to bear in mind is because of the, I'll say the maintenance envelope for the system, as you are pulling it apart and cleaning it, every manufacturer I have seen suggests that this assembled size is roughly 1/3 of the actual floor space needed to install one of these heat exchangers. Now, next up, we'll be going over keel coolers. Keel coolers are a somewhat simpler system. These circulate fresh water through external tubes or heat exchangers attached to the hull. Heat is then transferred to the surrounding water. This type requires no raw water intakes, reducing maintenance and risk of clogging or fouling inside your pipes. Now, for characteristics, the big one is your cooling effectiveness is somewhat dependent on vessel speed. As you start to move underway, more seawater will start to flow over your keel coolers and you'll get an increased cooling effect. This is somewhat useful as when you're stationary, you won't be using likely as many systems or your main engines will not be under load. So it kind of scales with your speed. Now, as for advantages, it's excellent for operating in polluted or debris-strewn waters because there is no seawater intake. There's nothing to basically suck in extra water to get clogged up in sea chests or grating. Another big advantage, and the big one for me, was it minimizes the internal space requirements. However, one of the disadvantages is, as you are adding an appendage to the outside of your hull, there will be added drag due to the hull shape disruption. Now, as for a general explanation of your keel cooler and how it works, for this one, I'll start at your engine. As it's running, it's producing quite a lot of heat. Now, you have cooling water that circulates through the engine, and as it heats up and comes up to temperature, it'll leave through your thermostat and housing, moving down through your piping, through the hull, and into your keel cooler. Once there, the keel cooler will run this fresh water back and forth through various small tubes. This will allow it to very effectively dissipate heat into the seawater around it. Once it has made its way through the circuit and back up through the hull, it will have cooled off enough to re-enter the engine and cool it again, thus continuing the cycle. This is a general example of a diagrammatic of how you might fit a keel cooler to the side of a vessel. One thing of note is the very minimal plumbing you can see coming from the main engine to the keel cooler. No additional pumps, no separate circuits. It's fairly clean to install. Here is an example image of what you would see a keel cooler as on the side of a vessel up on dry dock. As you can see, it's simply a large rectangular box, essentially, with a bunch of back and forth running small tubes. Now, moving on to our last topic of the day, box coolers. These are heat exchangers located in recesses in the hull, like a sea chest. They act like keel coolers, but don't protrude from the hull form in the same way. As for advantages, first of all, they are more protected than keel coolers, making them much better for shallow operating vessels or vessels operating in heavy debris waters such as ice. And because they are recessed, there can be much less hydrodynamic impact compared to keel coolers. Sort of advantage and disadvantage is it does rely more on water convection to dissipate heat. And in the next slide, I'll explain that a little better. The only other disadvantage is they are a bit less effective for the same size heat exchanger area compared to a keel cooler. Moving on, this slide shows how a box cooler would be seated into a sea chest. And as you can see from the arrows moving up and through the cooling tubes, you can see that they really do rely on water moving through the sea chest to truly effectively dissipate their heat. This is the main reason they're a little less efficient than a keel cooler for the same size heat area. The other consideration, I'll say, with box coolers is because they are recessed, and especially because the water in there will be a little warmer, this can be a trouble spot for marine growth, mussels, barnacles, anything of that sort. So they will need to be accessed fairly regularly for cleaning. Now, in conclusion, based on the information I covered, as well as additional specifications and calculations that I went through, I chose to use keel coolers for my vessel, largely because of the minimal internal space requirements. Some other benefits of moving from plate heat exchangers to keel coolers would involve, would be the reduced number of pumps, as there is no seawater circuit involved in this type of cooler. With this comes a lowered electrical load and reduced maintenance. Overall, I felt that this was a good fit for my project vessel. And somewhat as a sidebar, I did really enjoy the extra research that went into this, as it wasn't really covered in the course material as much. It was nice to sort of get a new challenge and work around it. Very good. Now, that all said, are there any questions? Yes, sir.
Great job, Fred. I have a question though about with the keel cooler, I think it was, the diagrammatic area, like where the engine is so close to the shell, and it's kind of just like sticking up into the actual cooler pump. I was wondering, are there any like standards based on like how far your engine would have to be off the shelf for like maintenance envelopes and whatnot? 'Cause I mean, it seems like it's a pretty tight swing.
That will depend mostly on the actual hull shape of your vessel. If you have fairly flat sides, you can recess it, and you really just need enough room to be able to access any of your mounting hardware that might be in around on the hull side. Other than that, that's the only real limitation of how close you could mount them to the side of your hull. Okay, anything else? David.
You didn't have as much space in your engine room as you needed to fit any of them.
That is a good question. I really only explored other options because I couldn't fit the recommended plate coolers into my engine room. So I probably wouldn't have explored other options simply because I would have completed the system and it would have worked. Winston.
Thanks, Fred. I was just wondering what sort of information the manufacturer supplies you with.
I can't speak for every manufacturer, but the one that I reached out to was very helpful in working alongside sizing and speccing certain keel coolers that would work. And they did give me a range based on how I wanted to route the piping, and especially what kind of waters you would be traveling through. But no, they did work very closely alongside, and they did a lot of the heavy lifting. So I will have to say that it was very nice to work with them. Lovely. Yes, Mark. Relatively costing, not so much. I was given a general range for keel coolers depending on which model I went with, and the big one was how far away it was from certain machinery, simply because they would want to come and oversee some of the install and probably provide and spec a lot of the valves and piping for it. Anything else? Yes, John. Yes, it did. It does offer a section on if you're using a traditional, say, two-circuit heat exchanger, or if you're using a fuel cooler, box cooler, something like that. There weren't many changes, truthfully. The gensets were the biggest option, where they had a different model that simply routed their piping differently for a keel cooler. But the main engines, there wasn't much change at all. Yes.
Are they all relatively the same size?
Mhm.
And so just wondering, are they all of the same parameters within that?
No, there are many different sizes, and it typically depends entirely on how much cooling you need. How much heat you need to be able to dissipate will determine the overall length or width of the fuel cooler. Now, the main thing there is you can specify, where you would want to mount it on your hull, and they'll try and fit it within that length or width. But it depends entirely on, say, how much heating you need and where you can fit it. Yes, sir.
Thanks for your presentation. So first off, our fuel cooler, so that's one for me. Just curious, is it dependent or as much dependent on the temperature of the seawater compared to conventional fuel systems with changers, some of that, so, operation if the vessel is working in tropics versus, is there any impact there?
I can't give a definite answer across the board, but from what I've seen, the general temperature of your seawater was a factor, but only slightly more than a traditional, say, two-circuit system that just pumps seawater through. Yes, sir. Mr. Strobridge.
How does your regional layout ensure
The main things that I did to try and ensure that there was good access was spacing equipment out so that you could get in and around as many things as possible. The main items were the gearbox and main engines, which couldn't move around because it has a traditional shaft. But other than that, everything else was spaced around so that your average person could easily pass through and access each side of the equipment wearing, traditional overalls or gear you would expect. Nothing else? Lovely. Well, thank you very much for your time.
One actually go through the presentation, go down.
Thanks for that, Fred. Up next, we have Lucas Wiseman, who's going to be doing his presentation. Again, one of our AR students. Give him a Whenever you're ready there.
Hello, I'm Lucas Wiseman, and today I'll be presenting my naval architecture project for a medium-range product tanker called the SCI Monarch. So this is my presentation outline. I'll be walking you through the details of my vessel. This slide outlines the topics I'll cover, and I'll review each section one by one so you get a comprehensive look of my design process. So I'll be going through the mission profile, the state of the art, the hull development, the general arrangement, the powering and electrical. Then I'll be moving into the structure, the capacities, the trim and stability, then the cost estimate, and finally I'll do the capabilities and summary. So this is the initial steps and my design constraints. So my mission is to design a product tanker for Scorpio Tankers International that transports refined products, so gasoline, diesel, jet fuel, and biofuels with minimal route restrictions. This ship must meet IMO, SOLAS, Transport Canada, and Lloyd standards. During the design, I also made sure to address environmental, port, and economic limitations. This could include things like port draft restrictions. And I wanted to design a product tanker because of my interest in the oil and gas industry, and I also wanted to design a ship that could service the port of St. John's. So this slide shows the proposed route of my vessel. The home port is in Halifax, and then the tanker will visit St. John to pick up petroleum products and then drop it off to Boston. And then it'll go to Port Arthur in Texas to pick up American refined products, and then stop at St. John's and then back to Halifax. So next we'll go into my SOTA trends. These are just the details of my design. So first I conducted my state-of-the-art analysis using data from similar vessels. This comparison provided the groundwork for the design by examining the relationships between the deadweight, which is my design driver, and the length overall, beam, and block coefficient. These parameters were set based on my state-of-the-art, and they could have been later refined in the process. But this state-of-the-art ensures that my ship will be completed in the most economic and efficient way, as it has been done before. It's a fairly common design, so I'm not going to reinvent the wheel. This SOTA data is good data to go off of. So first I'll go into my length overall versus deadweight. So this helped me determine what the most common length overall was for ships of a similar deadweight. You can see that the data is pretty tight, as this is a very common size ship. It was pretty easy to tell that for 50,000 tons, my length overall should be around 183 meters, if not dead on. So this information greatly helped me determine the size of my tanker. So the next main dimension would be the beam. So this is also extremely tight for my 50,000 tons. I went with a beam of 32 meters, and this ensures that my ship will be able to handle the sufficient cargo loads of, like 50,000 tons. And this is also important for stability. Then there's my drop. So this is another relationship with the deadweight, as that is my driving design factor. Although this is a little bit harder to understand visually, it does suggest a draft of 13.2 meters. And
Anyways, we'll move on to my block coefficient, which is the last thing needed to determine my parameters. So this suggests a block coefficient of 0.78. So then the final parameters of the vessel are 183 meters length overall, then 32 meters beam, 13.2 meters draft, the block coefficient of 0.78, a depth of 19 meters, freeboard of 5.8 meters, a 60,127 ton displacement, my dead weight of 50,000 tons, range is 9,000 nautical miles, the endurance is 30 days, and then a crew of 22. So moving on to the hull details. This is a fully displacement monohull that features a parabolic bulbous bow for improved fuel efficiency, since the ship will be steaming for extended periods of time at a constant speed. A large parallel middle body was incorporated to maximize my cargo capacity. And since the tanker will be carrying petroleum and gas cargo, a double hull was important to use for spill protection in case of accident or emergency. The longitudinal center of buoyancy was positioned aft to enhance my buoyancy there, as most of my weight would be in the engine room concentrated, especially at lightship. In all, the target displacement of 60,127 tons was met, and my waterline length is 178.5 meters, and the block coefficient is 0.78. So next, I will go through my general arrangement. The GA provides an overview of the vessel's layout, showing the deck arrangements and my centerline profile. It demonstrates how my space is allocated for cargo, crew, and my critical machinery. So first, we'll have this is my large-scale view of my main deck and my centerline profile, but I'll walk through each one in detail. So this is my centerline profile, viewing the superstructure and the engine room. It shows a view of you can see the casing and the lifeboat there. We move on to my cargo distribution manifold, and you can see my cargo tanks there and the double bottom. Then going forward to the forecastle and the chain locker, you can also see the bow thruster compartment and the forepeak tank. Then moving down to main deck, we have some common spaces for the crew, some inner gas storage, some more deck stores, provision stores. I have my hospital and fire stations that are easily accessible, and there's an emergency escape in the way of the lifeboat there. Going forward to a top view of the cargo distribution manifold, you can see my pump house there with the sample storage. There's manholes there for access for cleaning and inspection of the tanks. Then showing under the forecastle deck, there's a forward fire station for if anything happens where the other fire stations can't access. And then there's paint store and workshop, and then there's my access to the thruster compartment via ladder. So go down to sheet 2. You can see my tank top there, and then the various decks going up. So here's my generator flat. This is just up from the tank top. This is a platform for the generators and some additional auxiliary machinery. There's a cutout there for the main engine, as that exceeds another deck above. And you can see my aft peak tank and the space there for my fuel tanks. Moving up to my MCR flat, I have my machinery control room, steering gear room, exhaust boilers, and oil fire boiler. There's an engine workshop with storage for spare parts. Then we move up to the A deck. So this is where I have my galley and mess, and my emergency genset is there alongside the casing. and I have a provisions hatch there for loading my provisions into the storage. And then there's my forecastle deck, which primarily shows my mooring arrangement. And then these are my accommodation decks and wheelhouse, so we'll go through them one by one. This is B deck, so there's single rooms for the crew, each having their own bathroom. There's a gym and a lounge. Then moving up to C deck, there's included day rooms you can see there for the master and chief, and there's another lounge. And then moving forward to my wheelhouse, where you can see the console, navigation, and charting table with a radio area, and then my wheelhouse top with various equipment and the mast. So next up, we'll look at powering of my vessel. Haultrop and Menon was used to predict the resistance, so then I can forward size my engine. The engine I chose was a MAN BMW G50 ME C10.7 Tier 3 engine. This is a slow-speed diesel producing 8,600 kilowatts. I selected 4 MAN BMW 5L23 30H MK3 generators, each producing 850 kilowatts with a total of 3,400 kilowatts for the electrical. And then additionally, I have a MAN TT 1200 bow thruster rated at 1,200 kilowatts to make maneuvering in tight spaces easier. This design complies with Lloyd's regulations and uses a longitudinally framed system. It's framed transversely at the extreme forward and aft ends where there's more curvature in the hull. It'll be built with Lloyd's grade A steel, and this design enhances strength and durability to handle heavy loads and contradict the global bending. This structure is important for my vessel as it will be carrying dense liquid cargo, and there will be 9 watertight bulkheads. Next, we'll go over the capacities of my tanker. As you can see in this slide, I have a view of half my vessel where each of the tanks is color-coded. Obviously, the cargo tanks are very large with an overall capacity of about 45,000 tons. The ballast tanks have a capacity of 24,000 tons, and they're arranged to achieve an even keel at the design draft. This is needed to replace the weight of the liquid cargo in an empty condition. These two capacities represent the largest of my ship, which was expected, and my heavy fuel oil, marine diesel oil, lube oil, and potable water rounded the tanks on my ship. These capacities were all done to ensure that my vessel can maintain its 30-day endurance. One challenge here was designing the wing tanks in a way that exceeds the 2-meter requirement while maintaining the required cargo capacity and tank constructability. So next, I examined several operating scenarios that my ship might encounter. So light ship condition, port departure, and port and arrival, and then mid-voyage. And then I did my minimum operating condition. Each of these were done at full load and partial cargo load. Each scenario meets including light ship, meets the IMO and Transport Canada stability standard, confirming safe operations under varying conditions that we might undertake. So one of the last aspects of the design was the cost estimate of building my vessel. The CARIAT method and similar ships were used to determine this cost. The total estimated construction cost is about 51.7 million USD, And the major costs include those for steel and machinery material. And after applying a 30% profit margin, the final vessel price comes in at roughly 67.2 million USD. This seems to be reasonable as the Hyundai Venetian shipyard in Vietnam has vast experience building tankers, so they have a pretty streamlined process. So finally, I want to highlight the capabilities of my vessel and things that make it unique. This design offers flexibility to adapt to different cargo and operating conditions. If markets shift or the ship, this ship can adapt to different cargo and operating conditions, and it can take on various routes. The optimized hull form reduces resistance and improves fuel efficiency while integrating propulsion system and integrated bow thruster allows it to be easily maneuverable in tight ports. And this vessel meets international safety and regulatory standards, ensuring reliable and cost-effective operations over its lifetime. And the optimized design will ensure that the ship is constructed as economically as possible while still delivering on its high performance. Thank you for your attention. Is there any questions, feedback?
Where you're transporting a lot of petroleum products, did you have to give thought to installing an inert gas system in terms of like your TA or anything?
So I did actually. I have a, well, I said I have inert gas storage there, but I also have, that's there to purge the tanks while they're being loaded and unloaded. So I did think about that in terms of storage. We didn't go too much into the systems, but the space allocation was key in this process.
Absolutely.
Yeah.
Noticed you had for your structural structure on the deck. What was the rationale reason for that?
Well, I was thinking since it's a tanker and there's a catwalk already implemented, you won't be doing, there's no operations happening on top of the deck, so it wouldn't prohibit it in that way. And by doing that, you'd allow the most space possible inside the tank, allowing me to meet my capacity. So I went with that method. And also some of the ships, similar ships I was looking at had that done as well. For sure.
Positive, you're operating snow and ice accumulation.
Yep. Yes, Sean? Thanks.
The question I got for you though is regarding the bow thruster.
Mm-hmm.
So the question I have really is, did you specifically size your bow thruster based on anything, or is it more along the lines of you go to starting from similar ships?
I went more with a starting point on similar ships. I had, like I said, I'm not the first one doing this, nor will I be the last. So looking at similar ships, all of them do range between 1,000 and 1,500 kilowatts. So I just went off of what I've seen in terms of my reference material. Thanks. Any other questions? Thanks.
Break. Actually, this one's going to be a little longer because we're waiting for people to show up. So we're going to reconvene at 3 o'clock. We'll finish up with the last couple of presentations. So come on back here in half an hour.
You're calling.
I'll deal with that. Yeah.
What do you think on your last one?
Is there a light?
Does this
Yeah. There we go. Got it. And here you go.
So do I just pull up the computer and then type down? Do you need cheaper? Hang on.
I had to laugh, but there's the dog. So it's not the same one, two knots of current. So the ground of that bar are that plastic mats. It's a red drive there in the anchor system. And this is the work part, which is slow. Support the transport. Got brought in by the sister shop on the red. There's the top. So we have. Yes. Yeah, it brought us in. This time. Yeah. For you. So that right current. Take. So that wasn't waves. The engines in these can't maintain this. It's no fair. You can't either. No. Just. They don't let me in, can I? It's bad for the engine. It doesn't work. It doesn't work. So, what do you do? Well, you run it hard. Oh, I was gonna say. Yeah, but if you gotta, so, for the discharge. We can use a heater or? Well, then discharge took about 10 hours. By the time the ballast to get those units on. So it just can't idle for 10 hours. Yeah, it can idle for an hour, but it can't idle for days. So, so I just got back on Thursday for that. And in the middle of that, I was down in St. Albans unloading these. They're in pen stocks for the dam, hydro dam down there. They're 17.2 feet. Yeah. We gotta get coffee. Yeah, oh, actually, there's something up there. Oh, is it? I don't know. Yeah, no, it was this morning. Oh, yeah. Budgets, we can only have coffee. Yeah, they were covering the glass mats. The whole system there. They were kind of cool. They're so fun. Yeah. We have a whole house. We had they're not.
Oh, look at my notes.
Aren't they supposed to be like?
I got Swifty on the fucking board. Yeah, so to actually go forward, you have to press the down button.
Let's go to a test.
Yeah. Like that, see? Yeah. Put on your Lumion video while I'm always here. Just put on Just put on there.
I wish I would have went like second. Waiting all day.
Did you ever see, letter reading about, there's a movie, Big Sam, not first or last. Oh, wait, this one, it's like, I don't do it, he goes, no legs. She's always been the place, so.
No. You just stare at me. Yeah, and then you'll make faces. Hello. I'll say yes. I would that. Oh, yeah, that's what. That's me. Hands. Yeah. I don't want you both. Right now. I'm later. I can't see it. Why? Because the screen is all over your face. Well, I think, what I'm, stay right here.
Yeah. Ready?
Thanks. Soon you know. She was so mad. It was over the concert. Okay. Pictures of it there.
Hey. You just like that?
Oh, yeah.
You got that grab cat, didn't you?
Oh, yeah. So it's not like-
Well,
Put that camera
yeah.
Sorry, this whole-
So, first off, you can tell it's pretty much, just go. Now you're on.
Oh, pretty cool.
Bingo. Yeah, no.
Times this.
There you go. No stress, it's
Is
not
this
that
already
serious.
plugged in on?
Yeah, so on is on the side there, so it's switched up, should be on, just like test the pointer,
Oh, I know, testing. I don't want
right button.
Yeah, okay.
You're good to go. I'm sure I'm on stage with the whole point. Hearts contained. Yes, boy.
Looks snazzy.
Well, she's a nice bowl.
It's St. John. It's St. John. Yeah, I don't like St. Oh, New Brunswick.
Yeah.
Oh.
Turn her on.
Yeah, that is. Yeah.
You ready to rock? Are you just waiting for us? Are you started already?
I got.
You guys have
She's like right on the ball. Yes, no kidding. Is this on? Okay, but you're ready.
Yeah.
I was gonna say, the grader needs to be here, the judge.
Yeah, Judge Judy, if you will.
Judge O'Brien.
Yeah, there you go.
Yeah, really? Yeah.
Hello, no, we don't want to do that.
There you go. Hey guys, thank you. Welcome back. We're going to continue on with our naval architecture technology and marine mechanical systems presentations. Yeah.
Sorry, on the screen.
Yeah.
Sorry, I have to stand up again. I don't know what. Get your steps in.
There you go.
Welcome. And first up, we have naval architecture technology. We have another ship design. By Mackenzie Pearson. Mackenzie, you did a tanker, yes?
Yep.
All right. So there you go. You're off to the races.
Thank you. Good afternoon, everyone. I'm Mackenzie Piercy. I'm from Harsh Content, which is why my tanker is called Harsh Content. And I did a 35,000 deadweight product tanker. So let's get into it. So this is just an overview of what I'm going to be talking about today. We're going to do a vessel introduction, hull design, general arrangement, power and propulsion, structure, capacities, trim, and stability, and a price estimate at the end. So first we'll talk about the vessel introduction. So this vessel is a handy-sized product tanker, 35,000 deadweight. It's built for Iver Ships, which is a company in the Netherlands that charters ships to other companies such as Irving, which is why this vessel is going to be chartered for Irving to join the fleet with the other Irving vessels, Acadian, New England, and the Nor'easter. So this vessel is 178 meters long, has a beam of 29 meters, draft of 10 meters, a depth of 16 meters, and it will travel at 14 knots. So this vessel is going to travel from St. John's, New Brunswick to Portland, Maine, and Boston, Massachusetts. It's going to carry gasoline and diesel. And specifically, sorry, one moment. It should be noted that this vessel will return to its home port in St. John empty because there are no exports between Portland or Boston that takes into St. John's that could be carried by a product tanker. So some design features of this vessel. It has a bulbous bow, as stated in a couple presentations today. There was a chart in the fall that will show if a efficiency is increased with a bulbous bow, and for this vessel, it will. So that was a good design choice here. It has a stern bulb to allow for a better flow into the propeller, especially since this vessel has a large parallel middle body. It's going to taper off quickly into the aft end for better flow. And it also has a bow thruster to allow for more maneuverability when it is in port. So now we'll move into the hull design. So first, we did a SOTA, a state-of-the-art analysis, compared to other tankers here. I used approximately 40 similar ships, and here are just some graphs showing my LOA to my deadweight and my speed to my deadweight, which shows that 178 meters and 14 knots are a good fit for this vessel. So here is my lines plan, and this lines plan was developed so that the hull would meet all of its cargo hold carrying capacities, and as well as reach all its performance criteria, like its speed, as for why a bulb was added. And therefore, this vessel is designed so that it can travel 14 knots. So now we'll hop into my GA. So here's just an overview of my GA. This vessel has 11 decks in total, including 2 engine room flats, and it has 12 cargo holds with 6 on each side. So we'll just go through starting at the bottom in the engine room. So here's my engine room with my engine, and it has 2 means of escape. Here you could also see the marine diesel oil fuel and the bottom of the slop tanks, and as well as the propeller and the shafting arrangement. So now we'll move forward to the tank top where you can see the double hull water ballast tanks as well as all of the cargo tanks, the bow thruster, and the 4 pink ballast tank. Moving into the lower platform. On the lower platform, there's a cutout for the engine as it takes up height clearance into both this platform and the upper platform. And you can see the continuation of the pump room as well as all the heavy fuel oil tanks and the continuation of the slop tanks as well. So to the upper platform, there's another cutout for the engine as I previously stated. Here we could see the 3 gen sets as well as the steering gear, freshwater, black water, gray water, any heavy or marine diesel settling or service tanks, and continuation of the heavy fuel oil tanks since this vessel does carry a lot of fuel. And now here we'll move on to the main deck in the aft end. So here you can see cut out for the gensets and any exhaust, continuations of staircases, the electrical workshop and just a general workshop, valve control unit, engine control room, fire room, engine change room, CO2 room, and the nitrogen gas generator room for the inner gas system. Now onto the main deck here, you can see the layout of all the piping arrangement for the cargo tanks, the manholes for the tanks, as well as the pipe manifold, and then the chain locker into the forecastle. And then on top of this is just highlighted the catwalk that's used for crew to transport around the deck without stepping on the pipes. Moving on to the poop deck. In the poop deck here, we have all of the mess and rec rooms for crew and officers separately. We have a cargo control room, an infirmary, the galley with any provisions, coolers, freezers, as well as the start of the casing with the garbage for like the incinerator for garbage. And here we have the forecastle deck, which just has the mooring arrangement with the chain locker and the windlass, and then some stairs that go down to the main deck. Now we have A deck. Here we have an AC room and cabins for on crew. There is 20 crew on this boat, but we have 23 cabins, so there are 3 spares in any case of cadets being on board. And then we'll go up to B deck. B deck, we have the smoke room, electrical engineers room, pump oilers, stewards, cooks, and then we'll have the 3rd and 2nd officers on this floor, and they have slightly larger cabins, as well as this is where you would get on your life raft equipment here. And now moving up to C deck, this is where the chief and the chiefs and the captains will be, and they have their own lounge as well, a conference room, and their own laundry supply. And there's also extra cabin here for the owner. Now we move up to the navigation bridge here, where we have our console, we have charting space, radio space, a fire locker, battery room, and a spare cabin as well. And then this is just above the bridge here where we have our mast and any other navigation equipment. So now we'll move into power and propulsion. This vessel is equipped with a WinGD 6RT Flex 50D low speed diesel with an output of 10,470 kilowatts. This was found using the Holtrop-Menon method, as mentioned by a lot of previous people today. It has a brake power of 9,212 kilowatts. And then with the electrical course we did in the winter, it was sized to have 3 main gensets, a MAN L23/30H and K.3 with an output of 1,345 kilowatts each. As well in that course, we sized an emergency genset, which is going to be a CAT C18 with an output of 358 kilowatts. Moving on to structure. This is what caused me the most grief this whole time. So this vessel is going to be longitudinally framed, and it switches to transverse in the extreme ends and the engine room. This was done because I found I had issues with spacing in the engine room when I tried to do it longitudinally. And this structure was all calculated with Lloyd's registry and is to be constructed with Lloyd's grade A mild carbon steel. It has a double hull, as it is a tanker, so for any collision or emergency that were to happen aboard the vessel, only the outside hull will be penetrated, hopefully, and no oil spill will occur. So here's just a section of one of the cargo holds with your deep webs, and you can see the double hole around the outside as well. And then just a section looking at the ship overall. So now we'll move into the capacities. So here I have shown all the different tanks within this vessel. The blue shows the ballast water, which was found as 17,500 tons. And of course, the dead weight was 35,000, so that's what our cargo will be, shown in the gray. We have HFO on this vessel for most of its transit time, and MDO for when it is going into port or when it's starting up. And those are 1,342 tons and 191 tons. And then we found the lube oil to be 5.1 tons and fresh water to be 44.8 tons. And this vessel has an endurance of 28 days, so it only has to fill up anything every 28 days. And I think within this 28 days, it can make 6 full trips. And now into trim and stability. So there were a lot of conditions that had to be done for this vessel, specifically because it does parts of its voyage half full or empty as well, not just fully loaded at all times. So the stability was done in accordance to IMO and Transport Canada. We did a light ship condition, and then a port departure full empty half, mid-voyage full empty half, and port arrival is full empty half. And it's to be noted that this vessel did pass in all of these conditions, thankfully, so she shouldn't sink. And the worst condition was found to be the port arrival with no cargo, as there is barely anything in the vessel. There's no cargo, and all of your fuel, everything is basically empty. So now we'll go into the price estimate. Now this was done as stated using the carry-it method, which is not that accurate these days because of inflation or any other things, and the coefficients haven't been updated since. So this was all based off of the steel, weight, machinery, installation, etc. Steel labor cost came out to be 6.1 million, machinery installation 4.1 million, outfit labor cost 4.8 million, steel material cost 8.9, machinery material 7.7, outfit material cost 4.3, and then the total estimated price is $62.6 million. If anyone wants to buy it, let me know. So some closing remarks. So some things that I would like to change about this vessel if I had the chance to. I would like to determine a way to increase this efficiency. I don't think I mentioned it. However, with the propeller and the system in this boat, it only has a 50% efficiency, which is common for boats like this. However, it would be nice to get it up there to save on some fuel. And as I said, structure was a pain for me. So I would like to revisit some of the structure in the superstructure, maybe add some pillars to increase some scantlings there to protect height. And with that, thank you all for listening, and do you have any questions? Yes.
Yeah, I have 2 questions there. First off, great presentation. My first question is with regards to like your cargo tanks. I see you have some slop tanks there, which collect any kind of debris or anything like that from cargo. What type of system did you consider employing onto your vessel for cleaning your cargo?
Okay, I looked into this in the fall, and there are quite a few methods you can use, but some of them are quite risky because it involves people getting down in the cargo holds, and obviously it's petroleum products, not healthy. So this vessel would have a sprinkler system where there are sprinklers on the crowns of the tanks, and then all of the fluid from that will just drain into the slop tanks after use.
My second question is more about structure. I noticed like back to on the topic of their cargo holds, you have instead of corrugated bulkheads, you have straight like flat bulkheads. Now, if you compare like a vessel like one I designed, for example, like corrugated is very useful for cleaning purposes. Another thing to consider too is like with the manifold, it might have a little bit of compressive force, and then with the corrugated sheet, it helps resist that. I was just wondering how come you decided to go with the flat bulkhead as opposed to a corrugated one or even square corrugated, for example.
Originally, I did have corrugated bulkheads, but as we went into the structure calculations in the winter, I consulted Winston on it, and he said that if there was nothing where it was showing that it would be a benefit specifically for this boat, it was better off to go with just regular bulkheads to help in my sake of calculating structure.
Speaking from experience, they are more difficult to calculate, so yeah.
Yeah. Thanks. Yes.
I noticed for your gas system, you were using a nitrogen generator. Was that a different piece of equipment
I didn't really dive that far into it because it was just, I knew it had to be there. I didn't know what specifically. And just for the time we had, I just was like, well, at least I left space for it and figured out the next bit. Yes.
In your generation, it seemed you have a smoke room?
Yeah.
Is that, was that inspired from like how the Louis Saint Laurent has a smoking lounge as well? Or?
No, it was just, I was using the Robert Maersk as a sample ship. I had a couple GAs for that, and they had one. I was like, well, obviously there's a no smoking sign on the front of the vessel.
Yes.
I was super structured, so I was like, you can't smoke somewhere, so might as well have space.
Yeah, that's right, guys.
Yeah. Any other questions? Yeah.
The question I have for you though, regarding the structure, you mentioned the
Mhm.
not abnormal, structural design. At this point in time, tend to be just kind of, I think I'm going to be this. It will change. It
Mhm.
changes many times. It's very structural designs, the iterations that it goes through. One thing I did notice though is that you have your void tanks, void spaces at the side of your fuel area. You carry more fuel than you're allowed to carry around.
Like to have against the hull?
Yes.
Yeah. Yeah. I'm not allowed to have any of my fuel against the hull, so.
You see that's
Yeah. Of course. Any more? Okay.
Still no question, but let everyone else go first and I come up short. Just had a thought on the area of operations, you have ice conditions to consider. You just,
It's like just outside. So like you could, but you could also get away if you didn't.
no, I have no other question. Gas structure, so.
I have a question actually. It's about the mirror gas. It's like what you mentioned with the nitrogen gas generator. Are you using both nitrogen and carbon dioxide, or is it just like kind of depends on the fuel you're using?
That's a really good question. Nitrogen, but there probably could be some research done to figure out which one. I wouldn't know specifically, because like I said, I didn't
Gotcha.
go into the specifics, but
Yes.
Yeah.
Thank
you.
All right, we have one more presentation to go while we're waiting for presenters to get all set up. I want to take a minute to say thank you to everyone who's supported these guys all year long, the capstone projects, for the ship design programs are unbelievable about the world. And it means a lot, all the support we've given to these guys over these last several months. As they prepare these designs and so on. And also like to thank somebody from industry for being here and Sean asking questions. And we really appreciate it. And the other thing we appreciate too about industry is giving these guys an opportunity while they're students to get out there and experience industry, just to make sure that this is actually. And they usually come back a little bit different. There's actually an industry out there. You know, you're supposed to know something about it. It means a lot. So thank you for that. And I don't know if you guys realize how much you guys supported each other too. I mean, we get to see, right? But there was even some cross-pollination going on where the systems guys were supporting the NARC guys, and we never see that.
Yeah. Sounds divided, yeah.
Yeah, but it's really encouraging to see that, and so great job. You guys all did a really great job. David, are you ready? And our final presentation is from the Marine Mechanical Design, soon-to-be graduate, David Bonfield.
No, I'm not ready. What's going on?
Not ready. I don't have any jokes.
You got us.
Okay. Thank you, Vince. Good afternoon, everybody. Thanks for sticking around this long. My name is David Bonnell. I'm a third-year Marine Engineering Systems Design student. And like Vince and Fred's project, we went a little bit of a different route. So today, I'm going to be discussing the benefits of a waste heat recovery system for marine vessels. Maybe.
Oh, you press the down button to actually go forward.
Yeah.
Is the dongle plugged in?
No. Ah, not good. Ah, perfect. All right. So quick overview of what we'll be discussing today in my presentation. Firstly, we're going to discuss what exactly is waste heat, and then what is a waste heat recovery system. Next, the operation of a waste heat recovery system and exactly how it works. Next, we'll talk about some applications of a waste heat recovery system, followed by the benefits of installing and operating a system. We're going to follow that with some real-world examples with real vessels that do have these systems installed, followed by my project vessel and an example with one of those. Some challenges and limitations that you might come across when owning and operating a waste heat recovery system. And finally, a conclusion with some time for questions at the end. So to begin, what exactly is waste heat? Well, on ships, engines burn fuel to create energy, which is then used for several things on board the vessel, like propulsion, auxiliary systems, and hotel loads. The process of engines burning fuel generates heat. This heat is then sent through an exhaust system on board the vessel. It's sent through large pipes and then to the exterior of the ship out into the atmosphere. This heat is considered waste heat because it is not being used for anything in particular besides polluting the environment. So what is a waste heat recovery system? It is a series of components that is used to capture this heat and reuse it for various other components on the vessel. It converts the wasted heat into electricity, steam, or hot water. This kind of technology has been around since the 1950s when it originated with land-based steam engines and boilers. It was then later altered to be able to be used in marine vessels about 10, 15 years later. The modern versions of the systems that you see today have been around since the early 2000s, and those are the kind of systems that we're going to be discussing today. The top picture you see there is an Alfa Laval gas economizer, which is a part of the waste heat recovery system. It's the Alberg Micro, which is the smallest version of the model that you can buy. It'd be used for much smaller vessels. And the bottom picture is the Alberg XW, which is the largest version of a gas economizer. This would be used for the largest kind of vessels that would require a recovery system, such as tank container ships and like bulk carriers. So how does this system work? Well, it can be broken down into 4 easy steps. First, waste heat is generated by the engine, and then the gas or the hot air and steam is sent through the exhaust system. A gas or heat exchanger or gas economizer will then capture this heat. The heat captured is then sent to either 2 places. It's either sent to a steam turbine where it will produce electricity, or it will be sent straight to the ship for service. The steam that is sent to the steam turbine will produce electricity, and then this electricity will be sent to various other systems on board. So what are some applications that this electricity is used for? The first one would be the power can be used for electrical loads, such as lighting for hotel operations, navigational equipment, and auxiliary systems such as pumps and treatment systems. The second would be using the steam to heat up either water for crew quarters or even for fuel, for vessels that require fuel to be heated before it can be put into the engine, specifically vessels that would be operating in colder climates, like here. Finally, the last source would be reducing the load on diesel generators for propulsion. So there's various benefits that are going to come with installing and operating a recovery system in your vessel. First one, you will reduce fuel consumption by roughly 5 to 15%, and that's depending on the type, size, and operation of your vessel. Second, you're going to lower your operational costs as less power is needed to be generated because you are just reusing the same power. You're going to lower your emissions like CO2, which is then in return going to help you meet environmental regulations such as IMO. And it's also going to help with your EEDI, which is your Energy Efficiency Design Index. And lastly, it's going to help extend the engine life on your vessel. So let's look at some real-world examples of vessels that do use these kinds of systems. To start, we have the Emma Maersk. It's a 400-meter-long container ship, which at the time was the largest container ship ever built. It was launched in 2006, and it's a part of Maersk's E-Class series of vessels, which is a large line of ultra-large container ships that were designed to set a new standard for energy efficiency and environmental regulations. According to Maersk, the waste heat recovery system on board this vessel is going to reduce fuel consumption and CO2 emissions by approximately 10%. It's going to generate an extra 8.5 megawatts of power, which, for context, that could power about 4,000 homes. And then it's also going to consume 35% less fuel per container, which is much better than the average container ship that was built and operated at that time. Next, we have the Azul Brisa. This vessel is a 300-meter-long bulk carrier built in Japan and delivered in 2014. This vessel is also equipped with a waste heat recovery system. It recaptures the heat and reuses it for other auxiliary systems on board, and then it also helps with lowering the power demand for the propeller shaft. Operation tests have shown a 5% reduction in fuel consumption and CO2 emissions for this vessel. This vessel is also a part of a energy conserving environmental regulations line of ships, but for this one it's for MOL, which is Mitsui OSK, which is a large Japanese shipping company. So next, we're going to have a look at my project vessel. My vessel is a 98-meter-long roll-on, roll-off ferry, and its main job is to carry passengers and vehicles to and from Fogo Island. She has a 19-meter breadth, a 4-meter draft, with a displacement of 4,400 tons. And installed on this vessel is 3 Wärtsilä 8L32 diesel-electric engines. These engines are going to supply all the power needed for propulsion and then every other bit of power used for all the other systems on board. 2 of the 3 engines is going to be operating at all times, with a third on standby. And that's going to give us a total power of around 8,700 kilowatts. My main objective with my project vessel was to create and install all the systems required for this vessel to operate, which includes, not limited to, because there's a lot, my tank capacity drawing, where I calculated the volumes of all my tanks and made sure, using Lloyd's and all the regulations, that they were placed and fitted in the right spots. My ballast system, where I arranged the pipe layout for the pumping and suction of all the ballast water needed for the vessel. And this also included selecting pumps, filters, valves, and ballast water treatment systems. Next was my bilge system, which also included laying out pipe and suction for all the dirty oil, and it needed to be made sure that it's taken to the right locations and put into the right tanks. Next is my domestic water system, where I created a diagram showing all the connections needed for all the showers, toilets, faucets, sinks, washers, and even coffee machines. My fire suppression system, where once again I laid out all the necessary piping to ensure that my vessel, under any fire or any condition, is rightly saved from the fire. And last but not least, my exhaust system. This is what we will be discussing now. So, for my vessel, with a waste heat recovery system installed, I will save approximately 5% in fuel consumption and roughly 5% as well in electrical loads for hotel operations. Using these savings, we can see how much fuel and electricity will be saved. My fuel consumption before I installed a waste heat recovery system was around 309 cubic meters. But with the waste heat recovery system installed, my fuel consumption dropped to about 284.5 cubic meters, saving us around 25 cubic meters of fuel. For my electrical loads needed for hotel operations, before a recovery system, I needed about 205 kilowatts to power everything involved. And with a recovery system, I will need closer to 184 kilowatts. There are a few challenges and limitations you might come across when installing and operating a waste heat recovery system. For example, because a waste heat recovery system is made up of multiple components and it's not one just big system, it's going to take up more space and weight than other systems would. So if you have a small vessel or your engine room is very compact, you might have a problem fitting these systems in. Secondly, if the vessel is already built, you're going to have some challenges integrating this system into the previous systems in the vessel, like your exhaust system or whatever other systems you want this additional power to go to. You're going to have to go back, redo the drawings, go back into the boat, probably cut it open, fix all the systems, and then you're good to go. Next, your vessel may not receive the full benefit of a recovery system if it's not operating at high speeds or high loads. And finally, the most important one, money. There are a couple different costs that you're going to run into when buying and operating a waste heat recovery system. The initial purchasing cost is extremely varying depending on the type, size, and layout of your engines. For a vessel with main engines, the price can vary from $1 to $5 million, again, depending on how many you need, how many engines you have, and how big these engines are. For a vessel with auxiliary engines like mine, the price is going to be closer to somewhere between $500,000 and $800,000. It's such a low drop because you don't need as much power and there's not as much power going through these systems. And then for maintenance and repair costs, the value will also depend on size, quantity, and layout of the vessel, but we're looking at a price range of somewhere between $10,000 to $25,000 a year. So let's have a look at some of these challenges and how they encountered my vessel. So first we have the space and weight constraints. Due to the large size of my exhaust, which is because this vessel was intended to have more engines, just smaller powers. So my casing is much bigger than it needs to be. So space and weight constraints is really not going to be an issue for my vessel. For integration with existing systems, this one's very easy for me. It's a project vessel. It's not built. It's not a real boat. So I don't need to worry about integrating the system with anything else. I just need to delete some lines in my drawings and do them again. This is actually going to be an issue for my vessel. I am going to receive limited effectiveness because my vessel is going to be operating at lower loads than some vessels would be. It's constantly going in and out of ports, so it's not maintaining a top speed for very long times. So I'm probably going to receive a 5% reduction in fuel consumption instead of the typical 8 to 10 that a lot of other vessels might receive. So a quick cost analysis of my vessel and some of the savings that I'm going to receive. With the installation cost of roughly $800,000, an annual maintenance fee of around $25,000, and a hopeful lifespan of around 25 years for the system, including interest, we're going to be looking at a total future cost somewhere around $2.46 million for the system in whole. Now we compare that with some of the savings that I'm going to receive with this system. The total price of fuel for a year without a recovery system is going to look close to $13.8 million. With the recovery system, however, the cost for a year of fuel is going to drop to 13.1, giving us a total savings of around $700,000. And you take that over a 25-year lifespan, and you've got around $17.27 million in savings. A little bit of quick math will show you that it takes roughly 4 years to pay off the total value of what this recovery system would actually cost. For most other vessels, it'd probably be a little bit quicker because they are operating at higher loads, so they're going to receive a better benefit than I would from this system. So a quick conclusion for my project vessel. Although it doesn't receive the full benefit of a waste heat recovery system, it's still very evident that this vessel is going to save fuel, money, and electricity. To conclude the entire presentation, waste heat recovery systems represent a key step towards greener, more efficient marine industry by allowing vessels to capture and reuse waste heat that would normally be lost. They significantly improve fuel efficiency and reduce operation costs. They also help vessels comply with strict environmental regulations, especially here in North America, where our rules are a lot more strict than other places in the world. And finally, using real-world examples like the Emma Maersk and the Azul Brisa, along with my project vessel and a cost analysis, it is clear that despite challenges, long-term benefits completely outweigh any limitations that you will encounter, leading to saved fuel, saved electricity, and most importantly, again, saved money. Here are some references I used, and thank you very much. Are there any questions? Yes.
My question is for one of your case vessels, the Emma Maersk, that 8.5 megawatt waste heat recovery system. Can you put that into more applicable terms, say homes powered?
Yeah, so most homes are, they don't really use like megawatts or kilowatts. You're looking at like kilowatts hour and megawatts hour. So to take that 8.5 megawatts, that's like an instantaneous savings. So over a full year, you're looking at, I think it was around 70,000 megawatts an hour. So it's about 4,000 homes that it could power over a course of a year, yeah.
I was wondering, with your waste heat system, does that include the waste heat boiler? I'm not sure if you mentioned that or not. Yes.
There is a boiler in my vessel, so it would include a waste heat boiler. I didn't talk much about it. I couldn't find a lot of applicable information for my vessel, but yeah, there would be a waste heat boiler as well. Yes.
Where you mentioned the waste heat recovery system mounts to your exhaust, would this affect the back pressure to your engines at all?
It would. Great question. So it's actually going to significantly increase the back pressure on your vessel. When I did my calculations, it was somewhere, I believe, around 400 millimeters, and that's water gauge. So to add a waste heat recovery system, again, depending on the size of your vessel and how much back pressure you have, I've seen some where it adds close to 200, so almost half. And then I've seen others where it's basically doubling the back pressure through your exhaust system. Any other questions? Yes.
Yes, very well. I like heat recovery systems very nice. The question I do have for you though is when you use a heat recovery system to add to your electrical available for your ship, is that considered redundancy? Right? Is that a piece that you say, okay, well now I'll have this much extra power because I'm more thinking about the side of, right, if that goes down, you still have power requirements. So does it give you redundancy or is it considered part of your power?
That I'm not really sure. I believe it would apply with redundancy just because you're getting that extra power. So you've just got a bit of a backup. So like my engines can run enough power and stuff to supply everything. But because I have this extra power from my recovery system, I can lower those loads on my engines. So if I did need that extra power, or the waste heat recovery system or something like that wasn't working, I can just crank the engines up and I still have the same amount of power. No problem. Are there any other questions? Mr. Lee?
In your research, did you find any other ships similar to yours?
I found a couple, but the information I didn't really believe. It was a little spotty. So I couldn't really find any like passenger vessels that were very close to my ship that kind of had the same thing going. Any other questions? All right. Thank you very much.
Once again, thank you for coming out and supporting these guys. The presentations were awesome. Well done, guys. And that concludes the presentation for this year. All right. Good job, man. 4 in the morning.